Hello there, and welcome to Life Beyond Seen. Tonight we're going to the middle of Siberia, to a lake so old, so deep, and so unusually alive that it seems to have spent millions of years quietly ignoring the rest of the world and getting on with its own business. Not in a dramatic way, not with storms every 5 minutes or monsters leaping from the water on schedule. It has done something much stranger than that. It has made room for life that exists nowhere else on Earth. That is not the kind of claim a place makes lightly. Most lakes are content to be lakes. They hold water, reflect weather, freeze when it is cold enough, host fish, annoy hikers with mosquitoes, and carry on. Lake Baikal, on the other hand, behaves like a place that read the normal instructions, set them aside, and decided to become its own biological world instead. It is the oldest lake on Earth, the deepest lake on Earth, and one of the most unusual freshwater systems ever studied. UNESCO describes it as about 25 million years old and around 1,700 metres deep, with roughly 20% of the planet's unfrozen surface freshwater, and notes that its age and isolation produced one of the richest and most unusual freshwater faunas in the world. So tonight, that is where we are going. Into a lake that has had a very long time to become itself. Into cold, clear water that reaches so far down that it sounds less like a lake and more like a patient geological decision. Into a place where tiny crustaceans, strange fish, giant sponges, and even a freshwater seal have ended up living lives that would make perfect sense to Baikal, and very little sense anywhere else. Britannica notes that the Baikal seal is the only living seal that exclusively inhabits freshwater environments, and it lives in Lake Baikal and nowhere else. Before we settle in, let me ask you something simple. Where are you listening from tonight? Maybe you're at home with the lights low and a blanket pulled up to exactly the level of commitment you feel comfortable with. Maybe you're halfway asleep already and hoping I do not suddenly raise my voice like an enthusiastic game show host. I will do my best to avoid that. Perhaps it is late where you are. Perhaps it is early. Perhaps you are listening from a city full of traffic, or from somewhere quiet enough that you can hear your heating system making tiny mysterious decisions in the wall. Wherever you are, I am glad you're here. And while you settle in, while the room gets a little quieter, and the day begins to loosen its grip, take a moment to imagine this place with me. Not a tropical lagoon with postcard water and somebody trying to sell you a fruit drink and a carved pineapple. Not a warm little fishing lake with ducks drifting by and a sandwich in a backpack. This is a vast body of cold fresh water in southern Siberia, stretched like a long dark seam in the landscape, bordered by mountains and forests, and holding within it a history so deep that most lakes do not even qualify for comparison. Many lakes form and disappear on geological timescales. Baikal stayed. It remained in place long enough for life to experiment, split apart, adapt, specialize, and keep going. That long stretch of time matters more than it might seem at first. When a place lasts for only a short period, in geological terms, life has less time to turn unusual. Species arrive, settle in, maybe adjust a little, and that is often the end of the story. But when a lake stays stable for millions upon millions of years, while also remaining relatively isolated, evolution gets room to work. There is time for populations to separate, time for strange body shapes to stop being strange and start being useful, time for survival in deep, cold, oxygen-rich water, to favour creatures that fit that environment more and more precisely, until you begin to get animals and other organisms that do not simply live in the lake, but belong to it in a way that would be hard to reproduce anywhere else. UNESCO specifically points to Baikal's age and isolation as the reason it develops such unusual endemic life, meaning species found only there. That word, endemic, is going to matter a great deal in what follows. It is one of those scientific words that sounds slightly formal and then turns out to be very useful. It means native to one place, and only one place, not common in one place, not especially beloved in one place. Only there. That can happen on islands, in remote valleys, on isolated mountaintops, and in very old lakes. Baikal is the kind of lake that encourages it. It has been compared to the Galapagos for freshwater life, not because it is small or tropical or full of tortoises minding their own business, but because its isolation allowed living things to branch into forms that remained tied to that one environment. UNESCO explicitly calls Baikal the Galapagos of Russia for this reason. Now, in a normal conversation, this might be the point where someone says, "All right, but how unusual can lake creatures really be?" Which is a fair question. Many of us grow up with a fairly modest lake vocabulary. There are fish, there are frogs, there may be reeds, there may be a bird glaring at you with entirely too much confidence. That is about the extent of it. A lake, in the general imagination, is not usually where biological oddity goes to show off. If someone tells you there are creatures found nowhere else on Earth, you probably picture a rainforest, a hydrothermal vent, or an island where everything either glows faintly or is rude to naturalists. Baikal changes that expectation very quickly. Its waters hold a large share of species that are endemic, and some groups there have diversified to a remarkable degree. UNESCO's conservation materials note more than 1,500 aquatic species, with a very high proportion found only in the lake, while research summaries describe Baikal's amphipods and cotoid fishes as famous examples of major diversification in an ancient lake. This is where the story gets especially interesting, because Baikal did not become extraordinary by being comfortable in the ordinary sense. Its water is very cold, its depths are immense, its seasonal rhythms are demanding, yet the lake is also famously clear, and unlike many deep lakes, oxygen is present far down into the water column. That matters because oxygen opens possibilities. It allows life to occupy depths that might otherwise become a kind of biological basement nobody wants to rent. Scientific work on Baikal repeatedly points to its high oxygen content throughout the water column, even at great depth, as one of the lake's defining physical traits. So instead of a simple story in which life clusters near the surface and leaves the depths mostly empty, Baikal offers many habitats stacked through the water and across the lake floor, each with its own pressures, opportunities, and ongoing evolutionary negotiations. And that means creatures can specialise. Some do well in open water, some on the bottom, some in shallower zones along the edge, some in conditions that would be harsh for most freshwater species elsewhere. Give nature enough time, enough separation, and enough environmental variety, and it starts producing solutions that look less like copies and more like original drafts. That may be one of the most remarkable things about Baikal. It does not merely contain rare creatures. It has functioned over a very long period, almost like a workshop for freshwater evolution. Not an orderly workshop, of course. Nature rarely labels the drawers and sweeps the floor, but still, a workshop. A place where lineages entered, adapted, split, and diversified into forms tied closely to one lake and its unusual conditions. Molecular and evolutionary research on Baikal's amphipods and fish has long treated the lake as a major case study in diversification within an ancient freshwater system. And because this is a calm evening journey, rather than a race through a textbook, we can take our time with that idea. There is no need to hurry past it. A place can shape life simply by lasting. That may sound obvious, but it is worth sitting with. We often think of evolution in terms of dramatic struggle, of sudden shifts, of disaster and survival. Those things matter. Yet there is another side to the story. Persistence matters too. Continuity matters. A habitat that remains available long enough can become not just a setting, but an active force in the making of uniqueness. Baikal had time to do that. While climates changed, glaciers came and went in the broader region, and whole landscapes shifted across ages no human being could ever fully picture. The lake remained a place where lineages could continue. Some studies have even argued that endemic species in Baikal survived severe ecological disruptions in refuges within the lake system itself, helping preserve and renew its distinct communities across long spans of time. That endurance is part of why the lake has such a quiet authority in science. It is not just impressive because it is large or deep. Plenty of places are large, plenty of places deep. Baikal is important because it combines age, depth, oxygen, isolation, and ecological complexity in one freshwater body. That combination is unusual enough that scientists treat it almost as a category of its own, not literally its own planet, though the local wildlife might be forgiven for thinking outsiders seem terribly uninformed. You can almost picture the meeting. A standard lakefish arrives with ordinary expectations. "Hello," it says. "I assume this is a lake." And Baikal replies, "Technically yes, but we're doing several advanced things here." That, in a very loose sense, is the situation. For the animals and other organisms living in Baikal, this has meant opportunities that do not come along often. A species that enters such a system is not simply trying to survive in generic freshwater. It is encountering a vast, very old, very structured environment with physical conditions unlike most lakes, and with empty ecological roles waiting to be filled over immense spans of time. Some groups responded by diversifying spectacularly. The amphipods, small crustaceans that many people would never notice unless specifically introduced, are one of the classic examples. Research has described hundreds of endemic Baikal amphipod species, occupying a wide range of forms and ecological roles. That is the kind of detail I enjoy very much, because it politely upends human vanity. We tend to assume that only large, dramatic animals count as evidence of nature's imagination. A bear? Fine. An eagle? Certainly. A whale? Absolutely. But tiny crustaceans quietly diversifying into an extraordinary evolutionary radiation in a Siberian lake over millions of years? That somehow gets less attention at dinner parties, which is a shame, because it is one of the great stories of persistence and adaptation on Earth. And Baikal did not stop there. Its sponges are another striking example. In most people's minds, sponges are already filed under things I vaguely remember from school and perhaps from a bathroom. Yet in Lake Baikal, freshwater sponges include endemic groups that form a major part of the benthic biomass, meaning a major share of life on the lake bottom. Studies on Baikal sponges describe the endemic family Lubomyrskiidae as especially important and distinctive within the ecosystem. Then there are the fishes, including the famous Baikal cotoids, whose diversification has attracted scientific attention for decades. Again and again, Baikal produces the same basic pattern. A lineage enters or persists in the lake. Time passes, conditions remain unusual, ecological opportunity exists, and eventually the result is not just a resident species, but a cluster of highly specialized forms that make sense within Baikal's environment and look startlingly specific from the outside. The deeper you look, the more the lake starts to feel less like a container and more like a long-running conversation between geology, water, climate, and life. The basin itself is part of a rift zone. The depths are real depths, not just the flattering sort a tourist brochure claims after a generous measurement. The water is not only cold, but also remarkably clear. Seasonal ice plays a role. Rivers feed in, while only one major river, the Angara, flows out. And within that physical setting, creatures have had countless generations to settle into very narrow ways of living. UNESCO identifies the lake as part of the Baikal Rift Zone and emphasizes the scientific value of the ecosystems that develop there. This is also why Baikal tends to inspire two reactions at once. The first is curiosity. What exactly lives there? How did it get there? Why did it turn out that way? The second is respect, because once you realize how much unique life the lake contains, you begin to understand how much history is stored in those waters. Not human history this time, though there is plenty around the region. Biological history, evolutionary history, millions of years of survival, separation, adaptation and fine-tuning, all held inside one cold inland sea that has no interest in being ordinary. That phrase, inland sea, is sometimes the one that feels most natural when people try to describe Baikal emotionally, even though it is a lake. It carries the scale of something larger than our usual mental picture, not because the definitions are unclear, but because human intuition was not designed for a freshwater body that is deeper than many people can comfortably imagine, and old enough to make entire mountain ranges sound recent by comparison. Still, it is a lake, and in some ways that makes the story even better. Because lakes to many of us seem familiar, safe, understandable. Then Baikal enters the room and quietly raises the standard. So as we move further into this journey, that is the frame to keep in mind. We're not looking at a random collection of strange animals gathered by coincidence. We are looking at the result of long isolation, immense age, cold, clear water, unusual depth, and a structure that let life keep experimenting for a very long time. The creatures found only in Lake Baikal are not there because the lake is merely scenic, or large, or remote. They are there because Baikal has spent millions of years being exactly the sort of place where uniqueness can accumulate instead of vanishing. And that is where the story truly begins, because before we can meet the creatures themselves, before we can spend time with translucent hunters, eccentric bottom dwellers, giant sponges, and a seal that somehow ended up making a freshwater lake its entire world, we need to understand the setting that made them possible, not just the map location, not just the impressive measurements, the deeper reason this lake became different. Because Baikal did not simply host unusual life. First, it became the kind of place that could make unusual life feel at home. To understand why Lake Baikal could become a home for creatures found nowhere else on Earth, it helps to stay with the place itself a little longer. Before the strange fish, before the translucent hunters, before the freshwater seal that seems to have taken a very wrong turn and then committed to it completely, there is the lake. Not just as a body of water, but as a physical fact on the map. A very large, very old, very serious fact. Lake Baikal lies in the southern part of eastern Siberia, within Russia, between Irkutsk Oblast and the Republic of Buryatia. It stretches for about 636 kilometers, or 395 miles, making it less like the neat round lake many people imagine, and more like a long, narrow inland body of water laid across the land in a great curved line. Britannica describes it as about 31,500 square kilometres in area, with an average width of about 48 kilometres, while UNESCO identifies it as the oldest and deepest lake in the world, at around 25 million years old and about 1,700 metres deep. That setting matters because Baikal does not sit in some soft, crowded, heavily urbanised landscape where its edges blur into suburbs and parking lots. It sits in Siberia, and Siberia has a way of making distances feel honest. The lake is surrounded by mountains, forests, river valleys, and long reaches of land that still look large enough to remind a person that maps tend to flatten experience. Britannica notes that the lake occupies a deep structural hollow ringed by mountains, with some peaks rising more than 2,000 metres above the lake's surface. So when people hear Lake Baikal, they're not just hearing the name of a famous lake, they're hearing the name of a whole setting. Cold air, forested slopes, ice in winter, villages along the shore, long trains crossing Siberia at a respectful distance, water that does not behave like a casual weekend lake, water that has scale, and scale changes everything. A pond belongs to the weather of the day. A huge lake begins to influence weather around itself. Baikal is cold, of course, but Britannica notes that its climate is milder than the surrounding territory, with average winter air temperatures around minus 21 degrees Celsius and average August air temperatures around 11 degrees Celsius. In other words, the lake is not just sitting passively in the local climate, it is helping shape it. Large bodies of water do that. They hold heat, release it slowly, and soften extremes along their margins. That is one of the first useful things to picture. Not just a lake in Siberia, but a lake large enough to have a kind of presence. Large enough to modify local conditions. Large enough that even when winter takes hold, it does not simply freeze at the first rude remark from December. NASA notes that Baikal's sheer volume allows it to retain summer heat well into autumn, which is why it rarely freezes early. Formation usually begins in late December, and by mid-January the lake is generally ice-covered, with the last northern ice often lingering until late June. That long ice season is part of the lake's identity. For months each year, Baikal becomes something many lakes never quite managed to become at such scale. A frozen landscape that still contains a vast active world beneath it. The surface hardens, the air turns sharp, and the lake starts looking less like water and more like an enormous piece of blue-white geology. Yet underneath that ice, life goes on. Oxygen remains available in the depths, the water remains in motion, and the ecological story does not stop just because the surface has changed costume. USGS describes Baikal as well oxygenated throughout its depth, despite being more than 1,600 meters deep, which creates unusual habitats for freshwater life. Now, one small point is worth slowing down for because the phrase ancient water sounds simple, but it can be misleading if taken too literally. The lake is ancient, the basin is ancient, the system is ancient, but the water itself is not one single fixed batch that has been sitting there unchanged since long before humans learned to do paperwork. More than 330 rivers and streams flow into Baikal, and only one river, the Angara, flows out. So the lake is constantly being renewed while still remaining the same lake. That may sound odd at first, but it is true of many enduring natural systems. A forest can be ancient even while its individual leaves are temporary. A city can be old even though few of its bricks are original. Baikal is ancient in that larger sense. Its structure, its basin, and its continuing ecological history are old beyond ordinary comparison, even as fresh water continues to enter and leave the lake. I like that distinction, because it makes the place feel even more real. It is not a sealed museum exhibit. It is a living system with movement, inflow, outflow, storms, currents, freezing, thawing, erosion, sunlight, and long biological continuity. In that way, Baikal is old without being static. It keeps changing and keeps remaining itself. Its shape contributes to that feeling too. Baikal is not wide in the manner of an inland sea that opens outward in every direction. It is long, narrow and structured, with different basins and very uneven underwater topography. Britannica describes steep western slopes, gentler eastern ones, an intricate shoreline with major bays and inlets, and islands including Olkhon, the largest in the lake. That means life in Baikal is not occupying one single simple container. It is living in a place with corners, shelves, depths, peninsulas, deltas, exposed shores, sheltered bays, rocky stretches, softer bottoms, and seasonal differences from south to north. Even before you start talking about evolution, you can already see why a lake like this would not produce a dull ecological story. It has too many environments packed into one elongated body of fresh water. The Slenga River is especially important here. Britannica identifies it as the chief inflow, and the river system helps carry water, sediments, and nutrients into the lake. There are many other rivers as well, but the bigger point is that Baikal is connected to a very large surrounding drainage world, even while remaining unusual and isolated as a lake. It takes things in from a vast region, then sends water onward only through the Angara. It receives broadly, but releases narrowly. That is a useful image to keep in mind. It helps explain why Baikal feels at once open and secluded. And then there is the depth, which is one of those facts people hear so often that it risks becoming decorative. Deepest lake in the world. Yes, very impressive. But what does that actually mean when you sit with it for more than 5 seconds? It means the bottom is so far below the surface that ordinary lake comparisons stop being useful. It means pressure increases dramatically with depth. It means light vanishes. It means temperature and movement create layers and patterns unlike those in most smaller lakes. It means habitats can stack vertically in ways that open ecological possibilities over an enormous range. UNESCO gives the commonly cited depth of about 1,700 metres, while Britannica lists the maximum measured depth at around 1,620 metres. Either way, Baikal is not merely a deep lake, It is deep on a scale that changes how the entire system functions. USGS takes that story even further, because the visible lake is only part of the geological picture. Beneath the water lies a rift system and a very thick pile of sediments. USGS notes that Lake Baikal sits within an active continental rift, and that sediments in the lake exceed 7 kilometers in thickness, while the rift floor may be 8 to 9 kilometers deep. That is extraordinary. It means the basin is not simply a bowl scratched into the land. It is part of a major tectonic structure, one that scientists study as an analogue for the early stages of continental breakup. This is where the lake starts to feel less like a scenic destination and more like a long-term geological event that happens to be full of water, a very great deal of water. UNESCO says Baikal contains about 20% of the world's unfrozen surface freshwater, and Britannica gives the volume as roughly 23,000 cubic kilometres. USGS says much the same, adding that Baikal contains about as much fresh water as the Great Lakes of North America combined. That is not the kind of fact you absorb all at once. It needs a moment, one lake, one long Siberian lake, holding that much of the planet's readily available surface fresh water. It also helps explain the lake's clarity and reputation. Britannica notes that in calm conditions one can see down roughly 40 metres from the surface. For a lake of this size, that degree of clarity has always contributed to the sense that Baikal is not behaving quite like a normal lake. The water is famously low in mineral content and very clear. It gives the impression, in photographs and eyewitness accounts, of being both transparent and severe. Beautiful, certainly, but not in a soft, forgiving way. More in the manner of a place that expects you to notice how serious nature can be when left to itself for a very long time. And yet, despite all this seriousness, the lake is not empty or barren. This is important. People often associate cold with lifelessness, and that is one of those understandable mistakes the natural world keeps correcting. Cold places can be extremely alive. They simply require different solutions. Baikal's waters, its seasonal ice, its deep oxygenated layers, and its long continuity have produced not scarcity, but specialization. The cold is not an absence of life. It is part of the filter that shaped what kinds of life could succeed there. The location in Siberia contributes to that filter in another way as well. High-latitude lakes respond strongly to climate variation, and USGS notes that Baikal's latitude makes it especially sensitive for long-term climate study. Scientists have used its sediment record to reconstruct environmental changes across very long spans of time. That means Baikal is not only a lake full of life, it is also an archive. Layer by layer, the basin has recorded something about the changing climate and geological history of the region. That is one reason the phrase ancient water carries such weight. It is not only about age as a number, it is about continuity. Baikal has persisted long enough to become both habitat and record. Living species occupy it in the present. Sediments beneath them preserve traces of the past. The lake is doing ecology and history at the same time, which frankly feels a little showy, but in this case it has earned the right. If you were standing on the shore, the experience would probably not be one of instant fantasy. It would be one of scale, weather, and clean lines. A long horizon, clear air, mountains beyond the water, maybe ice depending on the season, maybe wind, maybe that particular kind of quiet large lakes can produce, where nothing seems to be happening, and yet the place never feels empty. There are settlements along the shore, ferries, roads, scientific stations and protected areas, but none of that reduces the impression that the lake belongs first to itself. UNESCO notes that the site is surrounded by protected areas and is valued not only for biodiversity, but also for scenic and natural significance. Olcon Island adds another layer to the geography. Britannica identifies it as the largest island in the lake, around 700 square kilometres, and it often appears in descriptions and photographs because it gives the central lake a stronger sense of scale and shape. Islands in a lake this old are not just scenery. They influence currents, shore conditions, habitats, and human experience of the place. The same is true of peninsulas like Sviatoy Nos and the many bays cut into the shoreline. Baikal is one of those places where the edges matter almost as much as the centre. There is also something useful in remembering that middle of Siberia is, for many listeners, less a precise coordinate than a feeling of remoteness. In strict geographic terms, Baikal is in southeastern Siberia, not at some neat measured centre point. But in the imagination, it sits at the centre of a certain idea of northern distance. A lake far from tropical clichés, far from warm water assumptions, far from the usual places people expect to find biological wonders. That imaginative remoteness has shaped Baikal's reputation for a long time, and in some ways it has hidden the lake in plain sight. People know the name. Fewer people know the full story. Perhaps that is because the lake does not advertise itself in the language most modern attention prefers. It is not colourful in the expected way. It does not sell itself through immediate softness. It is cold, elongated, restrained, and often monochrome. In winter it can look almost architectural. In summer it can still seem stern. But that reserve is part of the point. Baikal is not trying to charm you into noticing it. It is simply there, and if you spend enough time with the facts, the charm arrives anyway. The really important part, though, is what this geography allowed. A lake this large, this deep, this old, this oxygenated, and this physically varied was never going to be biologically ordinary. Once you place it in southeastern Siberia, once you understand the mountain ring, the hundreds of inflowing rivers, the single outflow, the long ice season, the clear water and the rift beneath it, the later story of unique life stops sounding accidental. It starts sounding inevitable. Not easy, not simple, but inevitable. Because now we're no longer dealing with a lake in Russia. We're dealing with a highly unusual freshwater system that has existed for millions of years in a deep tectonic basin under demanding seasonal conditions with enough stability to let lineages adapt over extraordinary spans of time. That physical setting is the groundwork for everything that follows. The creatures came later, the opportunity came first, and once a lake has had that much time in that kind of setting, it begins to do something most lakes never get the chance to do. It stops being merely a place where species live and starts becoming a place that pushes species to separate, adjust, and turn into something more specific to itself, which is where the story moves next. If Baikal feels like a world apart, that is because in several important ways it really is. Not another planet, obviously. The paperwork alone would be impossible. But in geological terms, ecological terms, and evolutionary terms, it developed under conditions that most lakes never get. It had unusual beginnings, it stayed in place for an unusually long time, and it offered living things an unusually broad set of opportunities. Put all of that together, and you do not just get a large lake with a few interesting residents. You get a freshwater system that gradually begins to behave like its own separate domain. The first part of that story begins under the water, far below the fish, the seals, the amphipods, and the winter ice. Baikal occupies a rift basin, which means the crust in this region has been stretched and fractured. Britannica describes the lake as lying in a deep structural hollow surrounded by mountains, and it notes that breaks in the Earth's crust produce hot mineral springs in the area, while severe earthquakes have occurred there in historical times. USGS is even more direct, calling the Lake Baikal rift system a modern analogue for the earlier stage of continental separation, and describing the lake as part of a large active continental rift in Central Asia. So Baikal was not formed by an ordinary shallow depression filling with water and calling it a day. It emerged in a tectonic setting that created immense depth, thick sediments, and a basin capable of lasting for millions of years. That matters because most lakes are temporary in the long history of the Earth. They appear, they fill, they silt up, they drain, they freeze, they change course, or they disappear entirely. UNESCO's summary of Lake Baikal emphasizes just how unusual this lake is, by noting that it is around 25 million years old and that most other lakes are vastly younger by comparison. In simple terms, Baikal did not just last longer than expected. It lasted so long that the usual lake timeline stops being a useful frame of reference. A habitat that survives for that long stops being a brief stopover for species and becomes a stage on which evolution can do much slower, more detailed work. That age is one of the main reasons Baikal became distinct instead of merely impressive. Imagine two lakes. One has existed for a short period geologically speaking. The other has remained available for tens of millions of years. In the younger lake, species can arrive, settle and adjust a little. In the older one, populations have time to separate, specialize and diverge. Traits that begin as small differences can become stable differences. Stable differences can become reproductive separation. Over enough time, reproductive separation can become a whole set of endemic forms. That is why ancient lakes are so important to evolutionary science. A review of speciation in ancient lakes notes that these systems are classic settings for radiations, and UNESCO explicitly describes Baikal as the Galapagos of Russia, because the evolution of aquatic life over such a long period produced an exceptionally unique endemic fauna and flora. Still, age alone is not enough. A lake can be old without becoming a separate biological world if conditions are too uniform, too unstable, or too connected to surrounding waters. Baikal became a world apart because age was joined by size, depth, physical complexity, and partial isolation. It is long, narrow, and divided into major basins rather than being one simple bathtub shape. USGS notes that seismic data show several subbasins with sediment packages several kilometres thick, while Britannica points to the lake's steep western margins, gentler eastern slopes, bays, peninsulas, islands, and variable shoreline. That means Baikal offers not one habitat but many, stacked and spread out through different depths and regions. Species do not simply occupy the lake, they occupy particular depths, shore types, basins, deltas, and water layers within the lake. This internal variety is easy to overlook at first, because people hear the word lake and imagine something fairly unified. Baikal is not unified in that simple way. Conditions differ from littoral zones near shore to the cold darkness of the deep. There are rocky areas, soft sediments, open water pelagic zones, river-influenced stretches, and places where seasonal patterns alter local ecology. Once you begin to think of the lake that way, as a large set of connected but distinct environments, the idea of diversification becomes much easier to understand. A species does not need to leave Baikal to find different conditions. In many cases, different conditions are already available within Baikal itself. Then there is the water itself, which is one of the big reasons the lake did not become just another cold deep basin with limited life below. UNESCO's conservation summary notes that, unlike many warm climate lakes, Baikal mixes thoroughly enough to carry cold, oxygen-laden water from the surface to the bottom. Another UNESCO summary says the waters are rich in oxygen even at the greatest depths, enabling fishes to populate all layers of the lake. That is a remarkable condition. In many deep lakes, lower layers can become oxygen poor, sharply limiting which organisms can live there. In Baikal, deep water is not merely an empty lower level, it is usable living space. That alone greatly expands the number of ecological roles the lake can support, and once deep water becomes livable, evolution gets more room to experiment. Deep habitats are cold, dark, and pressurized. Nearshore habitats are brighter, often more variable and structurally more complex. Open water habitats come with their own demands. Species that spread into these different zones do not face identical problems. Over long time spans, those different problems can produce different solutions. Research on Lake Baikal's endemic sculpins and amphipods has shown exactly that sort of depth and habitat-related specialization. A 2021 study on Baikal amphipods notes several endemic species flocks in the lake, including cotoid fishes and multiple crustacean lineages. while also pointing out that Sculpin visual pigments shift towards shorter wavelengths with increasing habitat depth. That is not a minor detail. It means even sensory systems have been tuned to the lake's unusual vertical world. Another reason Baikal became a world apart is that it was isolated in the right way. Not sealed off completely, because that is not how rivers and lakes usually work, but isolated enough for local evolution to take hold. More than 330 rivers and streams feed into the lake, yet only one major river, the Angara, flows out. That creates a kind of selective connection to the outside. Species can arrive, but the lake still functions as a distinct basin, with its own internal geography and long continuity. UNESCO highlights the role of age and isolation in the development of Baikal's unusual fauna, and the lake's famous endemicity reflects that history. Once species became established and adapted to Baikal's particular conditions, many of them remained tied to that system instead of blending back into a broad, ordinary freshwater network. What is especially striking is that the isolation did not only operate between Baikal and the outside world, it also operated within the lake. Genetic work on endemic Baikal amphipods found highly location-specific haplogroups, with genetic separation linked in part to geographic features such as the Angara outflow, the Selenga River delta, and different shore regions. In other words, even inside one giant lake, populations have not always mixed freely enough to erase local differentiation. That is exactly the kind of condition that can encourage ongoing diversification. A world apart does not have to be isolated by an ocean. Sometimes it is enough for a vast ancient lake to contain its own internal distances and barriers. There is also the question of competition. Ancient lakes often become special because early arrivals can diversify into many ecological roles before too many rivals crowd the stage. Baikal has fewer fish species than some of the old African lakes, but UNESCO's conservation material notes extraordinary richness in amphipods and flatworms, and it points out that nearly all of the amphipod genera there are endemic. This is important because it shows that Baikal's evolutionary story is not about one glamorous group taking over the headlines. It's about a whole freshwater system allowing many lineages, especially invertebrates, to radiate into roles that in other lakes might be sparse, occupied by different groups, or never develop at all. That helps explain why Baikal feels biologically self-contained. In a very ordinary lake, many species are familiar because they also occur elsewhere. In Baikal, lineages often seem to have taken the lake's raw conditions and developed their own local versions of how to be a crustacean, how to be a sponge, how to be a bottom fish, how to survive in deep cold water, and even, eventually, how to be a seal in fresh water. UNESCO's reports describe 2/3 of the living organisms found in the lake as occurring nowhere else, and one IUCN summary for the World Heritage Site states that about 80% of the aquatic organisms are endemic. Whatever exact percentage one cites from different summaries, the broader point is not in doubt. Baikal is dominated by organisms with a uniquely Baikal history. At that point, world apart stops sounding like a dramatic phrase and starts sounding almost conservative. The chemistry and clarity of the water added another layer to this separation. UNESCO's IUCN summary notes that Baikal's mineral content is 25 to 50% lower than that of many freshwater lakes, and attributes the lake's unusual water purity partly to endemic zooplankton such as Epischura, along with the rocky nature of much of the watershed. Clear water changes how light penetrates, how photosynthesis is distributed, how animals find food, and how visual systems evolve. Clear, cold, oxygen-rich water in an ancient deep basin is not a generic setting. It is a very specific package, and species that adapt to it can become increasingly specialized over time. This is also where Baikal's climate enters the picture in a serious way. The lake spends a long part of the year under ice, yet life continues beneath that surface. Seasonal freezing is not an occasional inconvenience there. It is a regular part of the system. NASA notes that Baikal typically begins freezing in late December and remains ice-covered for months, with northern ice sometimes lingering until late June. That kind of annual rhythm shapes breeding, feeding, movement, light conditions, and survival. Species that endure these conditions over vast timescales are not merely passing through a cold spell. They are built around it. There is a tendency, when people hear about unique species, to imagine evolution as a sequence of dramatic inventions. One strange mutation here, one bizarre adaptation there, and suddenly a place is full of curiosities. Real evolutionary history is usually slower and more practical than that. A population becomes slightly better suited to cold. Another becomes better suited to depth. Another becomes tied to a certain shoreline or food source. Gene flow weakens, differences accumulate. Selection keeps some changes and discards others. Over enough generations, what began as variation becomes separation. Ancient lakes magnify this process because the stage remains available for so long. Baikal's old age, internal habitat variety, and repeated opportunities for partial isolation created perfect conditions for this kind of steady divergence. It also helped that Baikal was not geologically dead. Britannica points to ongoing tectonic activity in the region, including hot springs and earthquakes, while USGS describes the basin as part of an active continental rift. An active system can alter shorelines, sedimentation, and local habitat patterns over time without destroying the lake itself. That is a subtle but important balance. Too much instability and habitat collapses before long-term diversification can take root. Too little change and ecological opportunities may remain limited. Baikal appears to have offered both persistence and change, a long-lived basin whose details kept shifting enough to open new conditions for life. Once you see all of these pieces together, the lake's history becomes less mysterious. It became a world apart because geology gave it a deep, long-lived basin. Climate gave it severe but regular seasonal rhythms. Water movement gave it oxygen at depth. Geography gave it internal variety and partial isolation. Time gave populations the chance to diverge. Evolution then did what evolution usually does when given enough room and enough generations. It started producing forms that match the place more and more closely. That is why Baikal cannot be understood just by listing superlatives. Oldest lake, deepest lake, largest reserve of unfrozen surface fresh water. Those are true, and they matter, but the deeper truth is that these superlatives interacted. Depth mattered because oxygen reached the depths. Age mattered because the basin endured. Isolation mattered because species could diverge. Internal complexity mattered because there were many ways to diverge. It is the combination that made Baikal what it is. Take away any one of those features, and the story would likely be smaller. There is also something a little humbling in that. Baikal did not become exceptional because it was trying to produce novelty. Nature does not have a marketing department. The lake simply persisted under very uncommon conditions and life responded. That response is what we now call endemic biodiversity. Scientists call some of its lineages species flocks or radiations. Viewers at home might simply call them wonderfully odd lake creatures. All three descriptions are pointing to the same reality. Over millions of years, Baikal stopped being just one place among many freshwater places and became a system with its own long private history of adaptation. And once a lake reaches that point, the question changes. It is no longer, why are there a few unusual animals here? It becomes, how many layers of uniqueness can one lake support before we have to admit that it has been running its own biological project for a very long time? In Baikal's case, the answer seems to be quite a lot. Amphipods alone number in the hundreds, with many restricted to the lake, and research continues to find fine-scale genetic separation, even within species that had once looked more uniform from a distance. The lake's distinctiveness is not only ancient, in evolutionary terms it still has detail. So when we say Baikal became a world apart, we do not mean that it floated away from Earth and began charging admission. We mean that the lake acquired the ingredients of long biological independence. It became old enough, deep enough, complex enough, and isolated enough for its living communities to stop reflecting ordinary freshwater patterns and start reflecting Baikal's own history instead. That is the real turning point in the story, because once that happened, the lake was no longer just a setting for life. It became an engine of specialization, and that makes the next part unavoidable, because a lake like that does not merely hold water. It creates rules of its own for everything trying to live inside it. By the time a lake reaches the kind of depth Baikal does, it stops behaving like a familiar lake and starts acting more like a system with its own terms and conditions. That is really what people mean, whether they realize it or not, when they describe Baikal as so deep that it creates its own rules. The surface may still shimmer in the wind, the shore may still look like shore, ice still forms, sunlight still falls, and water still moves in and out through rivers. Yet once you look below that upper layer, the ordinary image of a lake begins to fail. Baikal is deep enough, old enough, and physically unusual enough that life inside it is not responding to a single simple environment. It is responding to a vertical world. That vertical world begins with the most obvious rule of all: depth itself. Britannica lists Baikal's maximum depth at around 1,620 metres, while UNESCO gives the more rounded figure of about 1,700 metres in its general summary. Either way, the point is the same. This is not a lake where the bottom is a distant inconvenience for swimmers. This is a lake where the bottom is so far below the surface that pressure, darkness and temperature create a layered environment unlike what most freshwater species elsewhere ever encounter. Depth is not just a measurement here, it is the main organising force. Pressure is one of the clearest examples. At Baikal's greatest depths, the water column above an animal would create a hydrostatic pressure on the order of roughly 160 times surface atmospheric pressure, using the lake's measured depth and standard freshwater physics. No creature down there experiences that as a fun statistic. It is simply the reality of existence. Bodies, tissues, buoyancy, movement, and metabolism all have to work under that load. The difference between a shoreline habitat and a deep Baikal habitat is not a small gradient. It is a major physical divide. That is one reason species living at different depths can become so specialized that moving between those zones is not trivial at all. Baikal's depth makes the lake less like one habitat and more like a stacked set of worlds under one surface. Then there is the question of temperature, which in deep lakes is never as simple as cold at the top, colder at the bottom. Freshwater has the inconvenient and fascinating habit of being densest at about 4 degrees Celsius at the surface, while that temperature of maximum density shifts downward with pressure as depth increases. Britannica's overview of lake mixing notes exactly this pressure dependence, and classic work on Lake Baikal's deep water renewal explains that the lake circulation is strongly shaped by these thermobaric effects. That means Baikal does not mix like a shallow pond, and does not simply separate into upper warm life and lower dead cold water. It has a more complicated, more interesting system in which deep ventilation can occur because of the relationship among temperature, pressure and density. That may sound technical, but the biological meaning is straightforward. Deep water in many lakes becomes a problem because it is cut off from oxygen replenishment. In Baikal, deep water is renewed. USGS states that despite the lake's great depth, its water is well oxygenated throughout, and UNESCO notes that cold, oxygen-rich surface water is carried down to the bottom. That changes the rules immediately. In a more typical deep lake, the deepest levels may become limiting or even hostile for many forms of life. In Baikal, the lower depths remain available. Not comfortable by human standards, certainly, but available. A creature that can handle the cold, the pressure, and the darkness is not automatically excluded by lack of oxygen. That single fact opens an enormous amount of ecological space. This is one reason scientists have long treated Baikal as such a distinctive freshwater system. Its great depth should, in a simpler world, make it difficult for animals to occupy the lower reaches extensively. Instead, oxygenation and mixing help turn the depths into real habitat. Nature's response to that opportunity has been exactly what one might expect over millions of years: specialization. Species have evolved not merely to survive in Baikal in the general sense, but to succeed in particular layers and settings within it. Research on endemic Baikal fishes and crustaceans has repeatedly linked diversification to depth and habitat differences, with one study noting depth-related changes even in Sculpin visual pigments. The lake's physical structure is not background scenery. It is shaping evolution at a very fine level. Light adds another rule, and it is a strict one. Baikal is famously clear. Britannica notes that, under calm conditions, visibility can reach around 40 metres. That sounds wonderful until you remember the total depth. 40 metres is impressive clarity for a freshwater lake, but against more than 1.5 kilometres of water, it is almost nothing. Light can travel farther there than in many lakes, yet sooner or later it still disappears. The upper layer receives the sun, supports photosynthesis, and behaves in recognisably lake-like ways. Below that, the world narrows. At depth, sight becomes difficult or useless, colours lose relevance, and animals either adapt their visual systems to dim blue light, rely on other senses, or live where the surface might as well belong to another universe. That is an important correction to the mental image many people carry. Baikal is not simply a deep, clear lake, as though those adjectives sit politely side by side. It is a lake where clarity helps structure the upper water, while immense depth ensures that darkness still rules most of the vertical space. The effect is not just visual, it shapes food webs, timing, predation, and movement. Life near the surface can depend more directly on sunlight and seasonal blooms. Life deeper down must depend on material sinking from above, on predation, on scavenging, or on other pathways tied more loosely to the sunlit world. In practical terms, Baikal is one lake with multiple energy economies stacked inside it. Now add ice, because Baikal is not content with one dramatic physical constraint when several will do. NASA notes that ice formation generally begins in late December, with the lake largely ice-covered by mid-January, and northern ice sometimes persisting into late June. Britannica also describes the long freeze and the powerful moderating effect the lake has on the local climate. Seasonal ice changes light levels, surface exchange, movement and timing across the whole system. It is not a decorative winter accessory. It is one of the lake's major annual regulators. Species in Baikal are not simply living in a deep lake. They are living in a deep lake that becomes roofed over by ice for months at a time. And yet, once again, Baikal turns what might sound like a limit into one more organising rule instead of an absolute barrier. Because the lake remains oxygenated at depth, and because its circulation is not trivial, winter does not shut down the whole system in any simple way. Life continues beneath the ice. The surface world becomes harder, dimmer, quieter, but not biologically erased. For many organisms, these seasonal conditions are normal, expected, and built into their life cycle. In some cases, the very severity of the annual pattern may help reduce competition from less specialized invaders and reinforce the distinctiveness of the species already adapted to Baikal's rhythms. Currents and circulation impose their own rules too, though they are easier to miss because water movement in lakes does not advertise itself the way ocean surf does. Baikal has large-scale circulation, upwelling, downwelling, and complex regional water movements influenced by wind, river inflow, basin shape, and seasonal change. A review of Baikal's physical limnology describes cyclonic circulation and the ecological implications of those flows, while work on upwelling documents large cold water ascents from deeper layers that can affect the upper hundreds of meters. That means even within the same broad depth zone, conditions are not identical from one region to another. Temperature, nutrients, oxygen structure, and food availability can all shift with circulation patterns. For organisms living there, the lake is not still, it is active, and the activity matters. This is another sense in which Baikal creates its own rules. A shallow lake often responds quickly and simply to weather. Baikal is large enough and deep enough that internal dynamics have momentum. Wind forcing can influence deep ventilation and circulation in ways that climate researchers continue to study. And modelling work suggests that alterations in wind can significantly affect mixing and downwelling patterns. That is not just a matter for physicists with admirable patience and many equations. It is part of the reason certain habitats stay oxygenated, why nutrients move as they do, and how organisms encounter one another through the water column. The physics of the lake becomes the architecture of the ecosystem. Once you put these elements together, the picture becomes much clearer. Pressure sorts out who can live where. Darkness limits the usefulness of vision and the reach of sunlight. Thermobaric mixing and deep ventilation keep oxygen available far below the surface. Ice imposes long seasonal discipline. Circulation reshapes habitats and food supply. Clarity changes how light behaves in the upper water. Each one is a rule. None of them is optional. Every Baikal species is, in one way or another, a solution to that rulebook, and that helps explain why Baikal's endemic life is not just abundant, but often oddly specific. In a lake with simpler conditions, there are fewer ways to specialize. In Baikal, specialization can happen by depth, by shore type, by food source, by seasonal timing, and by local circulation pattern. UNESCO's conservation material highlights the lake's extraordinary endemicity, especially among invertebrates, and notes that almost all amphipod genera there are endemic. That is the biological signature of a system with many internal rules and enough time for organisms to adapt to them. The lake did not encourage generic survival, it encouraged tailored survival. It is also worth noticing that these rules do not affect all organisms equally. For a tiny planktonic creature, water movement may be destiny. For a bottom-dwelling fish, substrate and depth may matter more. For a sponge fixed to the lake floor, water quality, oxygen, and local conditions are everything. For the Baikal seal, the problem is different again, because now one of the lake's most famous residents has to solve not only deep cold water, but also ice, breathing space, prey location, and movement across a vast freshwater system. A place with strong physical rules does not produce one standard style of adaptation. It produces many styles, each narrow in its own way. There is a temptation to describe all this as harsh, and it is, but harshness is only half the story. Baikal's rules are demanding, yes, but they are also stable enough to reward specialization over immense timescales. That combination is powerful. If conditions are severe but wildly chaotic, highly specialized species may not last. If conditions are stable but too ordinary, fewer unusual forms evolve. Baikal sits in a remarkable middle ground. Its rules are strict, but they have been strict for a very long time. Life has had ages to negotiate with them. The result is not random oddity, it is long practice. This is why the lake can seem almost self-governing. Of course, the laws of physics are the same as anywhere else. Gravity has not taken a regional holiday. Yet Baikal combines those universal laws in such a distinctive local way that its ecosystem behaves on terms set largely by the lake's own shape and history. A creature entering that system cannot live as though it were in an average freshwater environment, because the environment will not allow that. Too deep, too cold, too clear, too seasonal, too oxygenated in the depths, too structurally complex. The lake insists on a particular style of survival. Even the simple contrast between surface and bottom becomes a kind of evolutionary corridor. Near the surface there is changing light, more direct contact with seasons, and stronger interaction with river inflows and weather. Far below there is steadier cold, enormous pressure, darkness, and different feeding opportunities. Between those extremes lie intermediate zones that are neither one thing nor the other. In a lake as deep as Baikal, those gradients are broad enough to support not just temporary occupation, but persistent specialization. Some animals remain tied to the upper waters, Others occupy the benthic world. Others move vertically or live in particular depth bands. Research on Baikal's fauna repeatedly treats this depth structuring as central to understanding how the lake's endemic communities formed. And because the lake is so old, these rules have had time to become written into bodies, not in the poetic sense, but in the plain biological sense, in pigmentation, in eye structure, in metabolism, in breeding behaviour, in body shape, in how an animal drifts, hunts, clings, burrows, filters, or avoids being eaten. Baikal's creatures do not merely occupy deep cold water, many of them have been shaped by it generation after generation, until their very form carries evidence of the lake's conditions. That is what makes endemic species so interesting here. They are not just residents with unusual addresses, they are records of the lake's rules made visible in living tissue. At this point, the phrase, "a lake so deep it creates its own rules," stops sounding dramatic and starts sounding descriptive. Baikal's depth changes pressure. Its depth and freshwater physics shape mixing. Its depth, together with clarity, structures the fate of light. Its depth expands habitat, and its oxygenation keeps that habitat available. Its winter ice alters the annual rhythm. Its circulation keeps the whole system moving in ways that smaller, simpler lakes never experience. The creatures living there are not simply adapting to Baikal as one broad condition. They are adapting to a layered world whose rules vary from surface to bottom and from season to season. That is why the next step in the story almost has to slow down and go underwater, because once a lake creates rules like these, the most interesting question is no longer the lake itself. It is what living things had to become in order to follow those rules and keep going in the cold, the clarity and the darkness below. And this is where the lake stops being impressive in the abstract and starts becoming inhabited in a very specific way. It is one thing to say that Baikal is old, deep, clear and oxygen-rich. It is another to imagine what it actually means to live there, day after day, generation after generation, in water that is close to 4 degrees Celsius in the deep zones, under high pressure, with very little light, through long winters of ice. A lake like that does not simply allow life, it filters life. It rewards certain designs, discourages others, and over a very long time it leaves behind creatures that seem less like ordinary freshwater residents, and more like answers to a difficult set of physical questions. Research on Baikal's deep-water sculpins describes those conditions very plainly. Low temperatures near 4 degrees Celsius, hydrostatic pressure above 160 atmospheres in the abyssal zone, perpetual darkness, and yet dissolved oxygen remaining high through the water column, because of the lake's unusual deep-water renewal. That is an unusual combination. In many deep lakes, darkness and pressure are joined by serious oxygen limits, which makes deep life far more restricted. In Baikal, oxygen changes the entire mood of the depths. UNESCO's reporting on the site notes that oxygen concentrations remain high even in the deepest waters, and USGS has described the lake as well oxygenated throughout its depth. So the problem for animals down there is not simply staying alive in chemically poor conditions, it is solving a different puzzle. How to function in cold, dark, high-pressure freshwater while still competing, feeding, breeding, and avoiding being eaten in a place where the lower layers are not empty at all. That may be the first great surprise of Baikal's underwater world. The depths are not a silent storage room beneath the real lake. They are part of the real lake. Fish live there, invertebrates live there, sponges grow there, predators move through different levels of the water. UNESCO's 2006 site summary notes that Baikal's oxygen-rich depths allow fishes to populate all layers of the lake, and it specifically points to large sponges growing in both shallow and deep waters, along with amphipods that diversified within the lake itself. Once you accept that, the whole mental picture changes. Baikal is not surface life plus empty dark water underneath. It is a vertically inhabited world. The cold is one of the reasons that world feels so different from most freshwater systems people know. Cold water slows things down. Growth can be slower, metabolism can be constrained. Reproductive timing matters, movement costs matter. In deep Baikal fish, the environment is not just chilly in a casual northern lake sense. It is stably cold at depth, and that stability has been there long enough for bodies to adjust to it over evolutionary time. The 2025 comparative transcriptomics study on Baikal sculpins describes deep water specialists as showing gene activity related to efficient energy use, cellular maintenance, and structural integrity, which the authors interpret as part of their adaptation to a high-pressure, low-temperature abyssal habitat. That is a useful reminder that adaptation is not only visible in what an animal looks like. A great deal of it happens in the quieter machinery of tissues and metabolism. Darkness naturally imposes another discipline. Baikal's upper waters are famously clear, with UNESCO and Britannica both noting visibility around 40 metres under good conditions, but 40 metres is almost nothing against more than 1,600 metres of depth. Clarity helps define the upper lake. It does not cancel the lower dark. Below the sunlit layers, visual life becomes more difficult, and that is where Baikal's creatures begin showing especially interesting adjustments. Work on visual genes in Baikal amphipods notes that studies of Sculpin visual pigments found absorbance maxima shifting towards shorter wavelengths with increasing habitat depth. The likely reason, according to that paper, is not simply matching whatever little downwelling light remains, but reducing photoreceptor noise so vision performs better in extremely low light conditions. That is one of those details that makes Baikal feel less like a lake and more like a very slow laboratory. Even the eye is being tuned for darkness, and not all creatures solve darkness in the same way. Some remain visual hunters where they can, some likely rely more heavily on other senses, on touch, movement, vibration, or simply occupying a feeding niche where waiting is as useful as chasing. Some rise and fall through the water column as light changes. Some spend their lives on or near the bottom, where the practical problem is less about seeing far than about functioning at all in a pressured, dim environment. Baikal's deep fauna is therefore not a single, deep water type. It is a collection of distinct answers to the same general problem. The sculpins alone radiated into about 40 endemic species, occupying a wide range of ecological niches, from pelagic to benthic, and from shallow to abyssal habitats, according to the 2025 review. That Sculpin story deserves a little attention because it is one of the clearest examples of how life in cold, clear darkness becomes specialised. Baikal's cotoid fishes are not an incidental side note. The same 2025 review says they make up as much as 80% of the lake's total fish biomass, and it describes their radiation from a common marine ancestor within roughly the last 2 to 2.5 million years. Over that time, different lineages spread into different depth zones and ecological roles. Pelagic species, according to the authors, show genetic patterns associated with sustained swimming. Deep benthic specialists show patterns linked to energy efficiency and protein homeostasis in high-pressure conditions. That is not the story of one fish species tolerating a big lake. It is the story of a fish radiation being sorted by depth, pressure, and habitat style, until the lake contains multiple distinct ways of being a Baikal fish. Some of the best-known examples are the Golomyankas, or Baikal oil fishes, which are peculiar even before you get to where they live. Britannica notes that the Golomyanka is unique to Lake Baikal and gives birth to live young. That alone is enough to make it memorable in a freshwater setting, but what makes it especially important in this part of the story is that it belongs to the pelagic world of the lake's cold depths and open water. It is one of the characteristic animals of Baikal's interior, not just its edges. The Golomyanka is also a major food source for the Baikal seal, which means that a fish adapted to this cold, transparent lake is helping support the only seal in the world that lives exclusively in fresh water. That food web is one of the nicest examples of how Baikal's darkness is not emptiness. The seal does not simply patrol the surface and hope for the best. Britannica notes that Baikal seals can dive to around 400 metres and hold their breath for up to 40 minutes while hunting Golomyanka, longfin Baikal sculpin, mollusks, and other invertebrates. PubMed's summary of the 2020 PNAS study adds an even stranger detail. Baikal seals also feed heavily on the tiny endemic amphipod Macrohectopus branicki, and the study reports that the seals catch these amphipods at exceptionally high rates, following their diel vertical migrations and using specialized comb-like teeth that let them expel water while retaining prey. So in the cold darkness of Baikal, a freshwater seal is effectively feeding on swarms of tiny planktonic crustaceans in a way that sounds more like a story from the ocean than from an inland lake. Macrohectopus itself tells you a great deal about life in this lake. UNESCO's site summary from 2006 describes it as a pelagic predator feeding on mesozooplankton and notes that it migrates vertically. The 2020 PNAS abstract calls it the world's only freshwater amphipod with a fully pelagic lifestyle. That is a remarkable sentence when you stop and think about it. Amphipods are often the sort of animals people do not expect to carry the emotional weight of a nature documentary. Yet here in Baikal, one of them has become not only endemic and planktonic, but ecologically central enough that seals pursue it by the thousand. This is what happens when a lake has millions of years to stop following ordinary freshwater expectations. Even the small creatures become specialists with very particular jobs, and there are many small creatures. UNESCO's IUCN summary for the basin notes around 1,500 aquatic species in the lake, with roughly 80% endemic, and it highlights the amphipods in particular, listing 255 species. It also notes 80 flatworm species, and remarks that an average European lake would have only a few amphipods and a small handful of flatworms by comparison. In other words, Baikal's darkness is not biologically sparse. It is crowded with local invention, especially among invertebrates. Life in these cold waters did not merely persist, it diversified. Some of that abundance remains out of sight simply because human beings are not naturally good at paying attention to microscopic or near microscopic life, unless it causes a rash, or appears under a microscope with dramatic music. But Baikal's ecological character depends heavily on such organisms. UNESCO's IUCN summary points to the endemic zooplankton Epischura as one reason the water remains so pure, noting that the lake's unusual clarity is maintained in part by this endemic plankton. That makes the story of the dark even more interesting, because the clear upper water and the dark deep water are linked by living filtration. The lake is transparent partly because its own endemic life helps keep it that way. In a sense, Baikal's creatures are not just surviving the environment. Some of them are helping maintain the very conditions that shape the rest of the ecosystem. That feedback is one reason the place feels so self-contained. Cold water carries oxygen downward. Endemic plankton help maintain clarity. Vertical migrants connect deep and shallow layers. Pelagic fish live in the open water. Seals hunt them and also target amphipods moving up at night. Bottom communities persist because the depths remain habitable. When you look at it that way, Baikal's ecology feels less like a chain and more like a woven structure. A change in one layer has consequences for another. The darkness does not sit apart from the sunlit world above it. Material sinks, animals migrate, predators follow, and the whole lake remains connected from surface to bottom. UNESCO's description of productive cold oxygenated water being carried from the surface to the bottom captures the continuity well. There is another useful correction to make here. Cold dark water often sounds hostile in a way that suggests life there must be desperate, reduced, or merely hanging on. In Baikal, many organisms are not barely enduring those conditions, they are built for them. The deep-water Sculpin study describes the abyssal habitat as harsh, but it also makes clear that Baikal's fishes have repeatedly colonized those zones and evolved different solutions depending on whether they are benthic or pelagic. The visual pigment work on sculpins and amphipods also shows that low light has not simply been tolerated, it has been actively shaped around by evolution. That is a very different picture from the idea of life cowering in the dark. You can see this especially clearly in the lake's bathymetric gradient, which sounds technical but describes something quite vivid. Life changing with depth. Near the shore and in shallower water, animals deal with more seasonal variability, stronger wave effects and more direct influence from river inflows and light. Farther down, conditions become colder, darker and more pressurized, but also in some ways more stable. Baikal's long age has allowed species to partition themselves along that gradient. The 2025 review says this diversification is especially evident by depth, with species adapted to niches ranging from shallow waters to the abyssal zone at 1,642 metres. So the lake does not simply have deep animals and shallow animals, it has a graded spectrum of residents tuned to very specific levels of the water column and lake floor. That matters for behaviour as much as for anatomy. Macrohectopus moves vertically. Seals track that movement. Golomyankas occupy cold open water and help sustain the seal population. Sculpins sort themselves through different depths and lifestyles. Even where direct observation is difficult, the lake structure implies a constant choreography of rising, sinking, hunting, drifting, filtering and waiting. Some creatures use the darkness as cover. Some use the clarity where light still reaches. Some depend on the flow of food downward from the upper waters. Some make their living along the bottom where organic material settles. The result is a lake that feels active even in the places where human eyes would see almost nothing. Winter changes that dance without stopping it. NASA notes that Baikal is generally ice-covered from mid-January, with northern ice sometimes lasting until late June. Britannica notes the same long frozen season. During those months, the surface becomes harder, quieter, and more isolated from the air, yet the underwater world remains in motion. Seals use breathing holes in the ice. Britannica says they cut those holes with their claws during the colder months before diving to feed. Beneath the frozen surface, the same vertical structure of the lake persists. Light is altered, but not erased. Oxygen remains available in depth. Predators still have prey to follow. A lake with so much winter ice might sound shut down. Baikal is better understood as rearranged. That long ice season may also help explain why Baikal's fauna has remained so distinctive. A highly seasonal, cold, structurally complex lake can be a difficult place for outside species to invade successfully unless they already fit its conditions very well. Endemic species, by contrast, are not arriving fresh and confused. They have generations of local adaptation behind them. UNESCO's summaries repeatedly emphasize the roles of age and isolation in producing Baikal's endemic fauna, and the physical severity of the lake likely reinforced that process by favouring residents already tuned to its rhythms. This is not the sort of water where generalists automatically thrive. Even so, Baikal is not a story of one perfect adaptation winning out everywhere. It is a story of multiple compromises. Pelagic fish must keep moving in open water. Benthic fish must handle the lake floor and local prey. Visual systems can be sharpened for dim conditions, but only within the constraints of the available light. Seals can dive deeply, but not indefinitely. Small planktonic crustaceans can migrate, but that also exposes them to predators tracking those migrations. Cold reduces some biological rates while making oxygen more soluble. Clarity helps some hunters and exposes some prey. The lake's conditions do not simplify life. They make it more exact. There is something quietly funny in that, because from above, especially in winter, the lake can look so still. Flat ice, pale light, long distances. A person unfamiliar with Baikal could easily imagine a kind of majestic emptiness, as though the place were all geology and no conversation. Meanwhile, below the surface, amphipods are moving, fish are sorting themselves by depth, seals are making calculated dives, plankton are helping keep the water clear, and deep benthic specialists are carrying on in cold darkness under pressures that would make most ordinary freshwater fish reconsider their life choices. The lake is not quiet because nothing is happening. It is quiet because most of what is happening underwater and without any interest in human applause. That is also why Baikal's darkness should not be mistaken for mystery in the vague sense. It is mysterious because it is physically hard to see and biologically specialized, not because it is magical. The conditions are clear: cold, pressure, low light, oxygen, seasonal ice, vertical migration, endemism. Those are very concrete things. Put them together over millions of years and you get an ecosystem in which life has become local, precise, and unusually inventive. The oddity of Baikal's fauna does not come from fantasy. It comes from long practical adaptation to a lake that gives no organism the option of being casual about where it lives. And once you look closely enough, you begin to notice that the largest wonders in Baikal are not always the largest creatures. Some of the most important work is being done by organisms small enough to miss entirely. Tiny zooplankton helping maintain clarity, small amphipods linking plankton and predators, specialized fish turning deep cold water into usable habitat, a seal making a living from swarms of little crustaceans by following them through darkness. In many ecosystems, the biggest animals take the spotlight and the smaller ones do the real engineering. Baikal is no exception. It simply makes that truth harder to ignore. So when we talk about life in the cold, clear darkness of Lake Baikal, we are not describing a few hardy survivors hanging on at the edge of possibility. We are describing a complete living system that has learned how to use the lake from the surface down through its great depths. Some species use the clarity, some use the dark, some move between them, some live by filtering, some by hunting, some by waiting for the sinking leftovers of the brighter world above. All of them are shaped by the same fact. Baikal's deep, cold water is not dead space. It is inhabited, structured, and old enough to have trained its residents into a set of forms you would not expect to find anywhere else. And that brings the focus naturally to the smallest residents first, because in a lake like this, the grand story of uniqueness does not begin with the largest fish or the seal, but with the little drifting organisms that fill the water long before most listeners would think to notice them, which is where the next part moves. Long before most people would notice anything unusual about Lake Baikal, before the seal, before the strange deep water fish, before the giant freshwater sponges, the lake was already being built from the small end upward. That is one of the easiest things to miss in a place with such dramatic measurements. We hear that it is the deepest lake on Earth, one of the oldest, and a vast reserve of fresh water, and our attention immediately drifts toward the large visible parts of the story. Yet the lake's uniqueness depends just as much on things that drift, filter, bloom, graze, and migrate in numbers too great to imagine and sizes too small to impress a careless observer. In Baikal, the tiny creatures did not merely arrive first in some vague historical sense. They started everything ecologically. They built the food web, helped maintain the clarity of the water, linked the bright upper world to the darker depths, and created the conditions under which larger, stranger endemic animals could exist at all. UNESCO's summary of the lake notes around 1,500 aquatic species, with about 80% endemic, and it singles out the endemic zooplankton Epischura as one reason Baikal's water remains so pure. That gives us a useful way into this section. When we say tiny creatures, we're not talking about one single group. We're talking about the basal machinery of the lake. Phytoplankton, especially diatoms, capture light and start the flow of carbon. Zooplankton graze on them and convert that production into animal biomass. Small predatory invertebrates feed on those grazers. Microbes process dissolved organic matter and recycle nutrients. Together, these organisms form the low, broad foundation of the Baikal system. A stable isotope study of the pelagic food web, summarized in a later ecological review, describes a fairly simple deep-water chain with 5 major groups. Phytoplankton, represented by the endemic diatom Aulacosera baikalensis. Mesozooplankton, dominated by the copepod Epischura baicalensis, macrozooplankton amphipods such as Macrohectopus branicki, carnivorous fish, and the Baikal seal at the top. That simple outline is useful because it shows how a huge ancient lake can still depend heavily on a few small endemic groups at the base. The first of those groups, the phytoplankton, does not usually get much applause. This is unfair but traditional. Microscopic algae rarely receive the same attention as seals with expressive faces or fish with unusual body shapes. Still, in Baikal they deserve a great deal of credit. Spring under ice blooms are one of the lake's classic ecological events, and one of the most important species involved is Olacosera baikalensis, a large freshwater planktonic diatom associated with these blooms. A JSTOR accessible study on the so-called Melocera years explains that this species can form major under ice blooms in spring, and it notes that its filaments may attach to the underside of the ice and sometimes exceed 10 centimeters in length, before sinking and contributing to both pelagic and benthic food webs. That is an extraordinary image once you stop and picture it properly. Beneath a frozen Siberian lake, long strings of endemic diatoms can hang under the ice, then drop downward to nourish the deeper parts of the ecosystem. Small things certainly, but hardly insignificant. Those blooms matter because they turn light into food at a time of year many people would assume the lake is asleep. It is not. Baikal has long been known for substantial biological activity under ice, and the Melocera years paper notes that under ice production can reach rates comparable to those of eutrophic lakes in some conditions. That is especially striking because Baikal is often described as oligotrophic, meaning its waters are generally nutrient-poor and exceptionally clear. In a less unusual lake, winter might suggest biological shutdown. In Baikal, winter often means the system is doing something complicated and productive beneath a surface that looks still and severe from above. The tiny producers are already at work. From there, the story moves to one of Baikal's most important residents, Epischura baikalensis. This tiny endemic calanoid copepod is one of the dominant animals in the pelagic zone, and it is difficult to overstate how central it is to the lake's identity. UNESCO's IUCN summary explicitly says, "The unusual purity of Baikal's water is maintained by one of its endemic zooplankton, Epischura." A later Lake Baikal ecology overview and long-term plankton studies tell much the same story in more detailed ecological language. Adult Epischura are able to exploit a wide range of phytoplankton, from very small cells to large diatoms such as Olacosera baikalensis, and their abundance helps structure the whole pelagic food web. A lake the size of Baikal remains so clear not only because of geology and hydrology, but also because one tiny endemic grazer is constantly doing its work in the water column. There is something almost comically humbling about that. If a person were asked to guess what keeps one of the clearest Great Lakes on Earth so clean, they might imagine mountain runoff, mineral balance, or cold temperatures alone. Those things matter. Yet part of the answer is that countless minute crustaceans are out there filtering, grazing, and quietly keeping the system in order. Baikal is not only a lake shaped by geology, it is also a lake maintained by appetite. Small appetite repeated in impossible numbers for a very long time. UNESCO's summary ties Epischura directly to water purity, and the deeper food web descriptions place it immediately above the phytoplankton as one of the indispensable middle links in the open water chain. That central position is why the phrase "started everything" fits so well here. The larger animals of Baikal are not feeding on sunlight directly. They are feeding on a system that has already been processed by microscopic algae and tiny grazers. Without diatoms and other phytoplankton, there is no foundational primary production. Without Epischura, that production is not converted so efficiently into a form available to higher consumers, nor is the water filtered in the same way. Without those first tiny steps, the rest of the chain loses its footing. A long-term study of Baikal's plankton records shows that the lake's basal food web has changed over recent decades with warming. including rises in chlorophyll A and shifts in zooplankton structure, which only reinforces how central these small organisms are. Change the tiny creatures and the whole lake notices. The next step up from Epischura brings us to Macrohectopus branicki, one of the most interesting small predators in the lake. It is an amphipod, not microscopic, but still small enough to belong firmly to the world of creatures many people would overlook until told otherwise. Yet it has become one of the signature pieces of Baikal's pelagic system. UNESCO's site summary describes Macrohectopus as a pelagic predator feeding on mesozooplankton, and the 2020 PENAS work on Baikal seal feeding notes that it is the world's only freshwater amphipod with a fully pelagic lifestyle. In other words, this is not a bottom-hugging little crustacean doing standard amphipod business in the shadows. It is a specialized open-water predator unique to Baikal, drifting and hunting through the lake's interior like a very small but highly committed answer to a very unusual ecological opportunity. That detail matters for two reasons. First, it shows that the small end of Baikal's food web is not just about producers and passive grazers. Even among the tiny or near-tiny animals, specialization goes a long way. Second, Macrohectopus is not just another inhabitant, it is a bridge species. The stable isotope description of the pelagic chain places it between Epischura and the carnivorous fish, and stomach content work summarized in later studies identifies it as a major prey item of adult Golomyankas, the lake's famous pelagic oilfish. So here again, the larger charismatic fauna depends directly on a small endemic invertebrate, occupying a very specific role that does not really have an obvious counterpart in ordinary lakes. This is also where Baikal's tiny creatures begin to look less like a support staff and more like the main cast. The pelagic food web described by Yoshi and later reviewed by Wader and colleagues is striking partly because it is comparatively simple at the major group level. You can sketch it cleanly: endemic phytoplankton, endemic Epischura, endemic Macrohectopus, fish, seal. That simplicity at the top level sits beside extraordinary diversity within the lower groups, especially among amphipods and other invertebrates. UNESCO's summary points to 255 amphipod species and around 80 flatworm species in the lake, numbers far beyond those of an average European lake, and it notes that the amphipod fauna includes roughly 1/3 of the world's freshwater shrimp-like amphipod diversity, with all but one genus endemic. Once again, the lake story becomes one of vast local invention at a scale human eyes tend not to notice first, and that diversity is still being revised upward in practical terms. A 2024 review of Baikal amphipod genomics notes that current taxonomies list more than 350 amphipod species and subspecies, and emphasizes significant cryptic diversity, meaning that even forms once thought straightforward may conceal additional hidden separation. That is worth lingering on because it tells you something very specific about how Baikal works. The small creatures did not simply diversify a little and then stop. They diversified so extensively and in some cases so subtly that scientists are still sorting out exactly how many distinct lineages are living in the lake. Even at the genomic level, the small fauna of Baikal carries the marks of long, deep specialization. It would also be a mistake to think only in terms of classic grazing food chains and ignore the microbial world. Lake Baikal's pelagic zone supports a substantial microbial food web as well. Reviews and metagenomic studies show high abundances of bacteria, microbial eukaryotes, and viruses, especially in the upper water column and under ice periods, and researchers have explicitly discussed trophic coupling between the microbial and classical food webs in the lake. A 2019 freshwater biology paper abstracted in search results notes that carbon from Baikal's well-developed microbial food web moves into higher trophic levels, while metagenomic work has described novel microbial lineages in the upper water column of this cold oligotrophic lake. So even before we get to the visible plankton and the small crustaceans, the lake is already being built and recycled by a busy microscopic economy. That microbial side of the story is especially helpful because it keeps us from imagining Baikal's base as a neat ladder. Real ecosystems are not usually neat. Material leaks sideways. Dissolved organic carbon circulates. Bacteria grow on exudates released by phytoplankton. Small protists feed on bacteria. Larger grazers feed on some of those protists or on the phytoplankton directly. A review discussing whether there is a microbial loop in Baikal points to close local interactions between phytoplankton and bacteria during ice melt and spring bloom conditions, even if some details remain harder to measure. In plain language, the smallest living things are not just beneath the food web, they are woven through it. Even the timing of the lake depends heavily on the tiny creatures. Baikal's annual rhythm is partly a rhythm of plankton. Long-term datasets, including the famous multi-generation Siberian monitoring program summarised by Hampton and colleagues, show that plankton distribution shift through time and with climate. The PLOS-1 study on vertical distributions notes strong deal vertical migration in several abundant taxa, including Epischura, Macrohectopus, and Golomyanka. That means the tiny creatures are not merely floating around waiting to be eaten. They are moving through the water column on daily cycles, balancing feeding opportunities and predation risk, and larger animals are responding to those movements. The tiny creatures do not just start the food web, they set its schedule. There is also a comforting practicality to the way Baikal's base works. Nothing about it depends on fantasy. The endemic diatoms bloom under ice because light, mixing and seasonal conditions allow it. Epischura thrives because it is well suited to cold pelagic grazing in this lake. Macrohectopus occupies the open water because Baikal offers a niche that made such a lifestyle possible over evolutionary time. Microbes recycle matter because that is what microbes do in every ecosystem, though here they do it in a cold, ancient, oxygen-rich lake with long winters. What makes the place remarkable is not that its base is magical. It is that the base is so specialised, so stable, and so intensely local. The small creatures are doing ordinary ecological jobs in highly unusual Baikal ways, and once that is in place, the larger endemic life begins to make more sense. The seal can be unique because the fish it eats are unique. Those fish can be unique because their prey are unique. Those prey can be unique because the lake has unusual producers, unusual grazers, unusual small predators, and unusual microbial dynamics. Baikal's grandeur is bottom-heavy. The foundation is where the originality starts. If the lake had ordinary plankton, ordinary small crustaceans, and ordinary microbial structure, it would be much harder to produce the visible endemic oddities people remember. The big wonders depend on the tiny ones. There is one more reason to give these little organisms proper credit. They also make the lake vulnerable. Because the base matters so much, changes in climate, temperature, stratification, nutrient flow, or the mix of endemic versus non-endemic plankton can ripple upward through the whole system. Long-term observations have documented warming of Baikal's surface waters, changes in chlorophyll and cladoceran abundance, and shifts in plankton depth distributions, while recent coastal studies report a reduced role for endemic species in some communities under warming and human pressure. That does not erase the ancient uniqueness of Baikal, but it does remind us that the smallest residents are carrying a great deal of the lake on their backs, metaphorically speaking, since most of them are much too small for actual lifting. So when we look at Lake Baikal and ask why it became home to creatures found nowhere else on Earth, the answer does not start with the seal, or even with the fish. It starts lower down, in the under-ice diatoms, the endemic copepods, the specialised amphipods, and the microbial communities that keep matter moving through clear cold water. These organisms establish the routines, the flows of energy, and the local ecological logic of the lake. They are the reason Baikal's great biological story begins in miniature. They started everything, not because they are the oldest living lineages in some simple literal sense, but because every larger success in the lake depends on them already being there, already doing their work, already turning this ancient water into a place where specialization can take hold and stay. And from that point onward, once the tiny foundation is in place, the lake becomes ready for the next layer of strangeness, because some of those small residents do not remain merely small pieces of the background. In Baikal, a few of them become some of the most unusual hunters and survivors the freshwater world has ever produced. Once the tiny foundation is in place, Lake Baikal starts producing animals that feel almost unreasonable in the best possible way. Not impossible, not mythical, and not invented by a naturalist who had been out in the cold too long, but unreasonable in the sense that they look like solutions to problems most lakes never even present. A transparent fish drifting through dark water, a pelagic amphipod acting like a freshwater version of open water krill, deepwater sculpins occupying habitats down to more than 1,600 meters, amphipods with strong body armor, keels and spines, diversified into one of the most remarkable crustacean radiations in any lake on Earth. Baikal does not just support survival, it supports forms of survival that look startlingly specific to itself. UNESCO's World Heritage Material describes the lake as rich in endemic amphipods, notes that Macrohectopus branicki is a pelagic predator that migrates vertically, and highlights the unusual deep-water fishes of the Golomyanka group in the cold, dark depths. Research on Baikal sculpins likewise describes an endemic radiation, occupying all depth zones of the lake, including the abyssal zone. The obvious place to begin is with the Golomyanka, because this fish is one of those creatures that sounds slightly invented even when described accurately. Britannica notes that the Golomyanka is unique to Lake Baikal and gives birth to live young, while UNESCO's Lake Baikal nomination text describes the big Golomyanka as a small, big-mouthed, scaleless fish with a light pink body so transparent that, through its tail portion, printed text can be read like through a piece of glass. That sounds like the kind of sentence that would have been improved by restraint, but the remarkable thing is that it came from an official nomination file rather than a tabloid in love with the word alien. The fish really is that unusual. It belongs to a lake where transparency, cold water buoyancy, and life in dim open water have all been useful for a very long time. What makes the Golomyanka especially important is that it's not merely strange looking. It occupies a central ecological role. The 2025 review of Baikal sculpins describes the two Chamaephorus species, the big and small Golomyanka, as secondary pelagic fishes that inhabit the entire water column of the open lake, down to maximum depths of 1,642 meters. The same review says they lack a swim bladder, perform extensive vertical migrations, do not form schools, and maintain themselves in the water column with neutral buoyancy and elongated broad pectoral fins. In plain terms, this is a fish designed for a life of drifting, hovering, rising and sinking through one of the deepest freshwater habitats on Earth, without the usual equipment many fish rely on for buoyancy. That already makes it feel closer to a deep-sea answer than an ordinary lake answer. The style of movement matters here. Many fish species feel easy to picture because they swim in a way that matches our expectations. They dart, school, cruise, or lurk. The Golomyanka is stranger. A developmental paper on the group describes Golomyankas as sluggish benthopelagic fish with large pectoral fins that swim passively in deep waters, while the 2025 review says they hover rather than behaving like highly active pelagic fish. That gives them an almost suspended quality, as though Baikal had taken the idea of a fish and adjusted it for quiet persistence in cold, transparent depths. They are not built for a warm, crowded, surface-chopped life. They are built for a large, dim, vertically structured lake where unnecessary exertion would be wasteful, and where neutral buoyancy can be turned into an ecological advantage. Their reproduction is part of what makes them such strange survivors. Britannica notes their live-bearing habit, and the 2003 developmental paper refers to the two Golomyanka species as viviparous. In a lake full of ice, long winters and unusual vertical habitats, Live-bearing may help bypass some of the risks associated with laying eggs in exposed or unstable conditions. I am making an inference there rather than stating a confirmed single-cause explanation, but it fits the broader biological pattern of reproductive strategies becoming tightly adapted to local environments. What matters for the narration is simple. Even the way these fish reproduce looks tuned to Baikal's very specific version of life. Their bodies reflect that tuning in other ways as well. The 2025 Sculpin review notes that Golomyankas lack a swim bladder, while comparative work on endemic Baikal cotoid fishes points to lipids as a major means of achieving neutral buoyancy in pelagic lineages such as Commiphorus. That is a very Baikal solution. Instead of relying on a gas-filled bladder the way many teleos fishes do, these fish make use of body composition and structure suited to cold, deep water and large pressure differences. It is one more sign that Baikal's wildlife is not improvising. It has had millions of years to refine itself, and refinement is not the same as delicacy. The Golomyanka may be transparent and soft-looking, but it is one of the defining survivors of the lake. It lives in cold water, ranges through huge vertical distances, and forms a major food source for the Baikal seal. Britannica identifies Golomyanka and longfin Baikal Sculpin among the seal's main prey, and the PNAS study on seal foraging makes clear that Baikal's predator-prey relationships are tied directly to the lake's endemic radiations. So the transparent fish is not an eccentric side character. It is one of the structural supports of the upper food web. The seal survives partly because the Golomyanka does. Then there is Macrohectopus branicki, which is smaller, harder to picture, and somehow just as remarkable. UNESCO identifies it as a pelagic predator feeding on mesozooplankton and migrating vertically. Scientific summaries go even further. A 2020 paper in Hydrobiologia calls it the only freshwater amphipod with a pelagic mode of life at all life stages, and the 2020 PNAS seal study calls it the world's only freshwater pelagic amphipod. That matters because amphipods, in most people's experience, are not the sort of creatures expected to dominate open water like this. Yet in Baikal, one line of amphipod evolution has done exactly that. It has left the usual bottom-associated image of amphipods behind and entered the lake's open pelagic world as an active predator. There is a pleasing stubbornness to that evolutionary move. Most lakes would never make such a lifestyle worthwhile. Baikal did. Research summaries describe Macrohectopus as one of the lake's major zooplankton consumers and an important prey item for fish, especially Golomyankas. Pensoft's 2021 ecology note calls it an active predator and compares its role in the lake to that of Antarctic krill or mysids in other systems. So this tiny hunter is doing two jobs at once. It's a consumer of smaller planktonic life, and it is itself a vital food source for larger endemic predators. That makes it one of the most important connectors in the whole Baikal food web. It is also, by all available descriptions, a highly peculiar-looking animal. Taxonomic summaries emphasize its unusual morphology, and the 2019 Taxonomic Review of Baikal Amphipods says its form is so peculiar that some authors have treated it as deserving its own monotypic family Macrohectopodidae. That is a strong signal that this is not just another amphipod with a slightly unusual address. It is one of those lineages that has moved so far toward a specialized role that even taxonomists have had to stop and say, in effect, all right, this has become its own sort of thing. The PNAS work on Baikal seals adds an even better twist. It found that seals hunt these tiny endemic amphipods at extremely high rates by following the deal depth changes of amphipod swarms. And the authors argue that this predator-prey interaction is profitable because of those dense, predictable movements. That means a large freshwater seal in Baikal is not just chasing fish in cinematic solitude. It is also exploiting concentrated swarms of a tiny endemic crustacean in a way that resembles marine feeding systems much more than the usual image of a lake mammal. Baikal keeps doing this. It keeps taking familiar freshwater categories and making them behave as though they have borrowed habits from the ocean without ever ceasing to be freshwater life. From there, it becomes easier to appreciate the broader amphipod world of the lake. UNESCO's conservation material highlights the amphipods as one of Baikal's most outstanding invertebrate groups, and multiple reviews describe them as a classic adaptive radiation. The 2024 Amphipod Genomics Review says current taxonomies list over 350 species and subspecies, while older UNESCO material cited 255 amphipod species and noted that almost all the genera are endemic. The exact count varies with taxonomy and ongoing revision, but the deeper point is secure. Baikal's amphipods are not a minor flourish. They are one of the great radiations of freshwater evolution, and they are not all sleek little planktonic forms. One of the striking features of Baikal amphipods, according to phylogenetic work summarized in a University of Michigan copy of a 2016 molecular ecology paper, is strong body armor in the form of keels and spines. The 2011 Zoologica scripter work on Acanthogomarus specifically refers to giant amphipod crustaceans from Lake Baikal, so alongside the almost transparent pelagic predators, the lake also produced heavily armoured, sometimes giant benthic forms that look less like the soft-bodied scavenger many people vaguely imagine, and more like something assembled by a careful engineer with a taste for protective over-design. That sort of armour makes sense in Baikal, a lake with many predators, complex benthic habitats, and very long evolutionary time is exactly the kind of place where defensive elaboration can pay off. Here again I'm drawing a restrained inference from the pattern, rather than citing a single definitive sentence of causation, but the pattern itself is well supported. Baikal amphipods display extraordinary morphological diversity, and that diversity includes pronounced spines, keels, and other body modifications linked to their many ecological roles. Over long timescales, such forms became normal within Baikal even if they would look extravagant in an ordinary pond. The Sculpins tell a similar story at the fish level. Lake Baikal's Sculpin radiation is one of its signature evolutionary events. A 1997 molecular study described 29 endemic cotoid fish species occupying all depth habitats down to over 1,500 metres, and the 2025 Comparative Transcriptomics Review describes the Sculpins as diversified across all depth zones, from shallow littoral habitats to the abyssal zone. These are not just variants of one small fish hanging around different corners of a lake. They are a broad endemic radiation sorted by depth, behaviour, feeding style and body form into many specialised lines. Some remained benthic, some became bathybenthic, some became pelagic, some solved deep water life through energy efficiency and pressure-tolerant physiology. Others moved more actively through the water column. That makes Baikal's fish fauna feel almost architectural. The deeper you go, the more certain lineages appear to have been shaped for exactly that level. The 2025 review notes that abyssal sculpins face temperatures near 4 degrees Celsius, hydrostatic pressures above 160 atmospheres, and perpetual darkness, while genetic analyses indicate adjustments related to energy metabolism, protein maintenance, and cytoskeletal integrity in deep specialists. So when we talk about strange survivors, we're not talking about a few dramatic surface oddities. We're talking about animals whose bodies and internal chemistry have been tuned to a vertical freshwater world that most lakes never even offer. In a calmer lake, far younger and shallower, such specialization might seem excessive. In Baikal, it is simply practical. The lake rewards precision. A species that can exploit a narrow depth band, a certain prey type, a low light condition, or a particular benthic surface can hold that role for enormous stretches of time. That is why the fauna seems so local and so exact. Even when two creatures occupy the same broad lake, they may still belong to very different Baikals. One near the ice and upper pelagic water, one along the bottom hundreds of metres down, one moving vertically at night, one filtering or scavenging among deep substrates. The same body of water contains many ecological lives. UNESCO's description of fishes populating all layers of the lake because of oxygen-rich depths captures that basic structure, and the Sculpin studies fill in how fully that opportunity has been used. There is another reason these animals feel strange. Many of them blur boundaries that we are used to keeping separate. The Golomyanka is a freshwater fish that behaves in some ways like a deep-sea pelagic specialist. Macrohectopus is a freshwater amphipod occupying a niche more reminiscent of marine planktonic crustaceans. The Baikal seal is a pinniped living exclusively in freshwater and feeding partly on tiny amphipod swarms. The lake's endemic radiations repeatedly produce what biologists call convergence or ecological parallelism. Freshwater organisms evolving roles and forms that remind us of marine systems, because the ecological problems are similar even though the setting is a lake. Comparative work on buoyancy in endemic Baikal fishes explicitly points to parallels between Baikalian pelagic species and Antarctic secondary pelagic fish lineages. That does not make Baikal a freshwater imitation ocean. It makes it a reminder that certain physical and ecological problems tend to produce certain kinds of solutions, whether they occur in saltwater or fresh. Darkness, open water, vertical movement, pressure changes, and the need for efficient buoyancy do not care very much about our preferred categories. Baikal simply provided these challenges in freshwater form, and then kept the system stable long enough for local species to evolve their own versions of the answers. And while the word survivor can sometimes sound dramatic, here it is accurate in a very literal sense. These species are surviving in a habitat that is cold, dark, highly seasonal, and vertically enormous. They are surviving not as generic tough animals, but as lineages that became intimately tied to Baikal's own rules. The transparent fish survives because its body, buoyancy, and reproduction fit the lake. The little pelagic amphipod survives because the open water planktonic world of Baikal made such a life possible. The deep water sculpins survive because the abyssal freshwater habitat remains oxygenated and stable enough to reward specialization. The armoured amphipods survive because the benthic world of the lake has had millions of years to sort out who thrives there and in what form. It also helps to notice that strange-looking does not necessarily mean rare in ecological importance. The Golomyanka, however ghostly it appears, is central prey for seals. Macrohectopus, however small, is a key planktonic predator and prey. Amphipods in general make up a vast share of the lake's invertebrate diversity and biomass. UNESCO's summaries emphasise the exceptional prominence of amphipods and the importance of endemic forms throughout the ecosystem. Baikal's odd creatures are not decorative. They are the operating system. There is something quietly satisfying in that. In a more ordinary setting, the strange animal is often the marginal one, a curiosity tucked into a corner. In Baikal, the strange animal is often doing major ecological work. The lake is built around creatures that would look improbable elsewhere, and because of that, the whole place feels self-authored. No one imported the transparent fish as a novelty. No one assigned the amphipod the role of freshwater open-water predator. No one sat down with a plan to create a seal that would chase tiny endemic crustaceans through Siberian water. These things happened because Baikal has had enough time, enough depth, and enough isolation for survival to become inventive, and that inventiveness does not stop with mobile hunters. Some of the lake's strangest long-term survivors are not even animals that move much at all. They stay fixed, grow slowly, and build living structures across the bottom in forms more often associated in our minds with the sea than with a Siberian lake, which is exactly where the next stretch of the story goes. What makes Lake Baikal's sponge story so surprising is that it takes something most people mentally file under quiet background life and turns it into one of the most important structures in the whole lake. When people imagine remarkable freshwater creatures, they usually think of fish, maybe seals, perhaps the occasional crustacean with a hard-to-pronounce name and an alarming number of legs. They do not usually picture forests of sponge rising from the lake floor. But that is exactly what Baikal has produced. Its endemic sponge family, the Lubomyskidae, is not a side note. Reviews of the lake's sponge fauna describe these sponges as forming the bulk of the benthic biomass. making up around 44% of benthic biomass in one widely cited estimate, and dominating large parts of the littoral zone. The same sources describe them as a vital part of the ecosystem, not decorative growths attached to stones for the sole purpose of being overlooked by distracted visitors. That alone is worth sitting with for a moment. In many lakes, the bottom is imagined as mud, stones, some plants near shore, a few burrowing animals, and a general sense that the interesting business happens above. In Baikal, the bottom in suitable zones can become something much more structured. The best-known species, Lubomirskia baikalensis, grows as a mat in shallower areas, but in deeper water it rises, branches, and can form dense stands. A 2021 review of bleaching in endemic Baikal sponges says this species can grow to over 1 metre and forms underwater forests at depths of roughly 8 to 15 metres. A broader freshwater adaptation review says the species increases in height with depth and can form dense aggregates and beds that provide habitat for other organisms. That is why the word forest is not just journalistic enthusiasm here. It is a practical description of what the structure looks like underwater. There is something immediately odd about that image, because forests are not what most people expect from freshwater sponges. Sponges are often imagined as small, squat, yellowish or beige forms in marine settings, or as things one remembers dimly from biology diagrams. Baikal sponges are large for freshwater species. The freshwater adaptation paper describes Lubomirskidae as growing to around 1 metre, while PubMed's summary of Lubomirskia baikalensis notes that it dominates the littoral zone benthos of the lake. In other words, these are not minor residents occupying an unobtrusive corner. They are some of the defining architecture of the nearshore lake floor. That architecture matters for a very simple reason. Structure creates habitat. Once a sponge grows up and outward, rather than merely hugging the rock in a thin skin, it changes the conditions around it. It provides surfaces, shelter, crevices, and water flow patterns that smaller organisms can use. The Freshwater Adaptation Review says L. Baikalensis forms beds that provide habitat for a range of other species. So these sponge forests are not only living organisms in their own right, they're also infrastructure. In a lake already famous for strange fish and eccentric crustaceans, the sponges are helping make room for many of those lives to happen. At the same time, they are doing something equally important and less visible. They filter water. The 2021 diversity paper on Baikal sponge microbiomes describes the endemic Lubomirskiidae as sedentary biofiltrators that play an important role in the lake's ecology. A 2019 PLOS ONE paper on sponge mass mortalities puts it even more plainly, saying sponges efficiently filter organic particles and plankton from the water column, and that this ecological function increases water purity and maintains water quality. That means Baikal's sponge forests are not passive scenery. Water is moving through them. Particles are being captured. The benthic and pelagic parts of the lake are being linked through the simple repeated act of filtration. This is one of those ecological realities that becomes more impressive the more calmly you think about it. A sponge looks still. It does not roam. It does not chase. It does not leap out of the water in a way that secures funding for a documentary. Yet it is alive in a very active sense. Water flows through its body. Suspended matter is removed. Microbial partners live inside it. Nutrients are processed, and the surrounding habitat is altered by its presence. When you place that activity not in one small sponge, but across a huge endemic sponge fauna, covering large areas of Baikal's littoral zone, the result is not simply some sponges. It is a major system for filtration and habitat building built directly into the lake floor. The green colour of healthy Baikal sponges makes that activity even more interesting. These are not plain, inert-looking freshwater masses. The 2020 Peer paper on healthy and diseased Lubomirskia baikalensis explains that the sponges live in symbiosis with diverse eukaryotes and prokaryotes, including chlorophyll-containing microalgae, and that these photosynthetic partners give healthy sponges in the photic zone their green colour. The 2019 Freshwater Adaptation Review adds that Baikal sponges depend on associations with bacteria and various chlorophyll-producing microorganisms, including green algae, dinoflagellates and diatoms. So the green forests beneath the water are not green because the sponge itself has decided on a more cheerful appearance. They're green because their bodies are full of symbiotic photosynthetic partners. That detail makes the sponge forest feel even more like forests, though in a very different biological sense. A terrestrial forest depends on light and photosynthesis. So, in part, do Baikal's shallow water sponge stands. Except here the photosynthetic work is carried by symbiotic microorganisms living within the sponge tissues rather than by leaves. The result is a cooperative structure: sponge body, internal symbionts, filtered water, attached position, steady cold conditions. It is less like a single organism acting alone and more like a managed partnership that has had a very long time to become efficient. That partnership also helps explain why these sponges can be so sensitive when the system goes wrong. If a healthy sponge depends on a stable relationship with microbial and algal partners, then disease is not just damage to one body. It can be a breakdown of an entire living consortium. The 2021 diversity paper says an ecological crisis has been observed in the littoral area of Lake Baikal since 2011. And it states that mass sponge death is one important sign of that crisis. The 2020 Piaget study describes diseased sponges as losing their green symbionts, becoming discoloured, and in some places dying in large numbers. The authors note that diseased sponges now occur throughout the littoral zone, and that the etiology of the disease remains unknown. That loss of green matters for more than appearance. The sponge is not just changing colour, it is losing part of the living arrangement that helps define its normal condition. The Piaget paper reports that healthy sponges have bright green colour associated with algae, while diseased and experimentally infected material loses that colour as the microbial community shifts and the green symbionts die off. The PLOS-1 study on mass mortalities likewise found that diseased sponges showed major microbiome shifts, and warned that massive loss of sponges could affect both benthic communities and water purity. So when a Baikal sponge forest begins to bleach or rot, the problem is not confined to a few damaged branches. It has consequences for filtration, habitat structure, and the organisms that live among or depend on the sponges. That is one reason these sponges are so important to the lake's larger story. They are among the clearest examples of how endemic life in Baikal is not only strange, but functional. The lake did not produce giant freshwater sponges because it wanted to be memorable. It produced them because a very old, cold, oxygen-rich, stable freshwater system offered the right conditions for a freshwater sponge lineage to radiate and become dominant. The Freshwater Adaptation Review notes that the Lubomirskidae colonised Lake Baikal around 3.4 million years ago and now represent a unique endemic lineage. Zuki's 2020 species paper describes the family as the most spectacular example of endemic radiation in freshwater sponges under Baikal-specific conditions. That is a strong statement, and it is hard to argue with once you have looked at what these animals became. What they became, in plain terms, is large, persistent, habitat-forming freshwater filter feeders, unlike anything most lakes can produce. The taxonomic story has shifted a little over time as species boundaries are revised, but recent sources consistently describe the family as endemic to Lake Baikal and distributed across several genera, with roughly the mid-teens in recognised species and subspecies depending on taxonomy. The 2021 Diversity Review lists 14 described species and 2 subspecies, while the 2019 Adaptation paper cites 4 genera and 13 currently accepted species at the time it was written. The exact number matters less here than the main point. The entire family is a Baikal story. These are not common freshwater sponges with one local variant. They are a distinct endemic radiation rooted in this lake. That radiation produced different body plans suited to different parts of the lake. Lubomirskia baikalensis is the best known branched form, and the one most often associated with underwater forests. The same 2021 review says Baikal intermedia is an overgrowing sponge that occurs at all depths, including the deep water zone, and identifies both it and L. baikalensis as the most widespread species. So even within the sponge fauna, Baikal has not settled for one template. Some species spread as crusts or overgrowths. Others rise into branching stands, and together they occupy a range of depths and substrates. That range matters because it shows how thoroughly the sponges have entered the lake structure. They are not only in one ideal shallow strip under perfect light and then gone. The Piaget paper says endemic Lubomorskidae dominate the littoral zone at depths from 3 to 35 metres and can cover close to 50% of the available surfaces there. The microbiome review says L. baikalensis occurs from 3 to 120 metres, while B. intermedia reaches all depths including deep water. A lake floor with that much sponge cover is not merely occupied, it is shaped. It is also shaped visually. A healthy stand of Baikal sponges in the photic zone does not look like dull matter lying low against stone. It can look like bright green branching growth rising from rocks, almost tree-like, only denser and stranger. This is why the phrase living sponges feels more important here than it does in a generic description. Baikal sponges do not hide the fact that they are alive. Their colour, their growth form, and their ecological activity make them feel like a living fabric across the underwater landscape. Even their microbial and algal partners are part of that visible life. The lake's physical conditions help explain why such forms could develop. Baikal is cold, clear, and well oxygenated even in deep water. Its nearshore shallows can still receive enough light for photosynthetic symbionts, while the deeper water remains cold and stable. The adaptation review notes that regions deeper than 250 metres stay around 3.3 to 4.3 degrees Celsius, and it describes high oxygen levels throughout the water column, combined with generally oligotrophic conditions. Those are demanding circumstances, but they're also stable ones. A lineage that learns how to live there has time to refine its way of living. The sponge forests are one expression of that refinement. There are also hints in their biology that Baikal sponges are not simply generic freshwater forms transferred into a large lake. The adaptation review notes a morphological adaptation in Lubomorskidae that stands out: the loss of the ability to develop gemmules, the tough resistant bodies many freshwater sponges use to survive unfavourable conditions. That suggests these endemic Baikal sponges have become specialised enough to abandon one of the classic freshwater sponge strategies. In a huge, stable ancient lake, they apparently no longer needed to live by the same short-term emergency rules as freshwater relatives elsewhere. That is a remarkable sign of how fully they have adapted to their long-standing environment. It also says something useful about the lake itself. Baikal did not merely allow marine-like body sizes and forest-like sponge stands. It allowed a freshwater lineage to become less typical of freshwater sponges in some of its strategies. That helps explain why the sponge story feels so unusual. These organisms are freshwater animals, but they behave ecologically in ways that make them feel closer to reef builders or benthic habitat formers from the sea than to the small temporary freshwater sponge patches most people would imagine. Baikal keeps producing this effect. Its endemic life often looks as though it borrowed the scale or structure of marine ecosystems while remaining entirely within freshwater. And because the sponges are so large and abundant, they become useful indicators of trouble. The 2022 Marine Pollution Bulletin study summarised in search results found Lubomorskidae baikalensis suitable as a bioindicator for assessing pollution in Lake Baikal. That makes practical sense. A large, attached, filter-feeding organism living for a long time in one place is excellent at recording what happens in the surrounding water and substrates. If the water chemistry shifts, if nutrient loads rise, if contaminants accumulate, or if microbial conditions change, the sponge cannot simply relocate to a more respectable neighbourhood. It has to absorb the consequences where it stands. The darker side of that is already visible. The 2018 Great Lakes research paper on the current state of Baikal sponge fauna reports that diseases were found across the lake and emphasises that sponge disease can cause irreversible disturbances to ecosystem functioning if mass mortality occurs. It also describes declines in abundance and the spread of disease across sites, including places beyond intense local human activity. The 2021 review says that in some regions, all observed individuals were affected. Even where exact percentages differ by site and year, the pattern is clear enough to be worrying. An organism that forms forests, dominates benthic biomass, filters water, and provides habitat is not something the lake can lose casually. That gives the phrase "forests beneath the water" an extra edge. Forests are not just collections of trunks, they are systems that hold other life together. When a land forest is damaged, birds lose nesting sites, insects lose host plants, soil shifts, water flow changes, and light conditions transform. Sponge forests in Baikal are different in form, but similar in consequence. Lose enough of them, and the littoral zone changes structurally, microbiologically and chemically. The Pelos 1 study says massive loss of sponges can affect both the structure of benthic communities and water purity, which is almost the underwater equivalent of saying the whole neighbourhood changes when the forest goes. There is something else quietly fascinating here. These sponges are among the earliest branching kinds of multicellular animals in evolutionary terms, yet in Baikal they have become one of the most advanced examples of ecosystem engineering in the lake. PubMed's Prog Mol Subcell Bile Summary notes that L. baikalensis gained special research interest, not only because it dominates littoral benthos, but also because of its biology at the molecular level, including genes involved in body plan formation and biosilica production. That scientific interest goes well beyond the needs of this narration, but it reinforces a broader point. These are simple animals in one sense, yet the outcomes of their long adaptation are anything but simple, and perhaps that is the best way to understand them. Baikal's living sponges are not impressive because they are flashy. They are impressive because they turn stillness into work. They stay put, but they filter. They look soft, but they build long-lasting structure. They are green because their tissues contain symbionts. They are ancient in lineage, but locally specialised in a way most freshwater sponges never become. They create habitat simply by growing, and they help maintain water quality simply by living the way they do. In a lake full of transparent fish and strange crustaceans, the sponge forests remind you that one of the most unusual survival strategies is simply to remain anchored and become indispensable. So by the time you picture those green branching stands rising from Baikal's rocky floor, the lake starts to feel even more self-contained than before. Its creatures are not just occupying water, they are building layers of habitability inside it. The tiny plankton support the fish support the seal. The sponge forests filter, shelter and stabilise the shallows where much of that life is rooted. And in a place that has had millions of years to keep refining its own terms, that makes the next step in the story feel even stranger. Because among all these highly local creatures, one stands out as the most unexpected resident of all. A seal living in fresh water, as though that had always been the most ordinary decision in the world. Of all the creatures in Lake Baikal, the seal is probably the one that makes people stop and stare the longest. A strange fish can be explained away, at least emotionally, by reminding yourself that lakes are full of fish, and some of them will naturally end up odd if you give evolution enough time and a very unusual place to work in. Amphipods, sponges and sculpins can be filed under the same general category of freshwater life, becoming unexpectedly specialised. But a seal is different. A seal arrives with baggage. A seal carries the whole weight of our expectations about marine mammals, salt water, coastlines, surf, sea ice, and the general idea that if you meet one, there ought to be an ocean somewhere nearby. Then Baikal calmly presents a seal living in fresh water in the middle of Siberia, and the mind has to do a little recalculation. Britannica describes the Baikal seal, Pusa sibirica, as the only living seal that inhabits freshwater environments exclusively, and modern genomic work still treats its presence in Lake Baikal as one of the long-standing biogeographic puzzles of the group. That is the heart of the mystery. Not whether the Baikal seal exists, because it very clearly does, but how a seal ended up here in the first place, and then became so thoroughly at home that it now feels inseparable from the lake. The animal is not a visiting marine species that occasionally wanders inland. It is endemic to Baikal. It lives there, breeds there, feeds there, and belongs there. Britannica notes that it inhabits the waters and coastline areas of Lake Baikal, and can also occur in some rivers feeding the lake, but its world is Baikal's world. It is not commuting to the Arctic on weekends. The first important thing to know is that the mystery is not fully solved in one neat sentence. Researchers are confident about some parts and still uncertain about others. The 2023 genome paper calls the origin of the endemic freshwater Baikal seal and its phylogenetic relationships a long-term biogeographic issue, and it says there is no definitive data showing exactly how seals migrated into this landlocked habitat. That uncertainty is useful rather than inconvenient, because it reminds us that Baikal is not only full of unusual life, it also preserves old questions. Some parts of the lake's history are still being reconstructed from genetics, morphology, behaviour, and geography, rather than from any tidy historical record. No one, unfortunately, was keeping a detailed travel journal on behalf of Pleistocene seals. Even so, some pieces of the story are much firmer now than they once were. The Baikal seal is closely related to the ringed seal, and modern genomic work supports that relationship strongly. The 2024 whole genome resequencing study reports that the Baikal seal is the closest relative of the ringed seal, with full support in its genome-wide phylogeny, and the 2023 Genome Assembly paper also treats the ringed seal as its closest relative, citing previous multilocus and mitochondrial studies. Science Direct's Encyclopedia summary says the Baikal seal was derived from a ringed seal ancestor in the Arctic Ocean rather than being a relic of the old Paratethys. So the broad evolutionary picture is no longer especially mysterious. The seal's roots are Arctic. The puzzle is the route and timing. That route is where the story becomes delightfully improbable in a very geological sort of way. The 2023 genome paper notes that Lake Baikal is connected to the Kara Sea in the Arctic Ocean through the Angara-Yenisei river system, and says the most plausible current view is that seal ancestors moved from Arctic waters along the Yenisei, or through glacial and ice-dammed lakes that existed in central Siberia during Middle Pleistocene glaciation periods. In other words, the modern landlocked seal may be the descendant of Arctic animals that entered a freshwater system through a now vanished set of northern pathways opened or transformed by glaciation and river connections. This is not a dramatic invasion story with a clear beginning and end. It is a long, slow biogeographic shift made possible by ancient landscapes that no longer exist in the same form. The timing remains debated. The same genome paper summarises earlier estimates ranging from about 2 to 3 million years ago, to 1.5 to 2 million years ago, to as recent as 0.4 million years ago, depending on data and method. Its own discussion says researchers are certain only of the Arctic origin, not the exact migration date. Meanwhile, the 2024 genome-wide phylogeny paper reports divergence estimates of roughly 1.15 to 1.7 million years ago and notes that the demographic histories of Baikal and ringed seals look shared until around 2 million years ago, which may mark the period of separation. So when people ask how long the Baikal seal has been there, the honest answer is not one precise number, but rather a range within the Pleistocene, probably on the order of hundreds of thousands to over 1 million years. That is still plenty of time to become very thoroughly local. Once you accept that a ringed seal-like ancestor likely entered the Baikal system from the Arctic long ago, the next mystery becomes less about arrival and more about persistence. How did a marine mammal adapt so completely to freshwater life? Part of the answer is that not all seals are equally tied to open marine coastlines in the way people imagine. Ringed seals already have a strong relationship with ice, isolation, and life in enclosed icy waters. The Baikal seal inherited or retains several Arctic-style traits that make much more sense when you remember that ancestry. The 2023 genome paper explicitly points to breeding on ice, white natal fur for camouflage on snow-covered ice, long underwater capacity beneath thick ice, and the instinct to breathe from pockets of exhaled air under the ice as evidence supporting an Arctic origin. The paper also notes that these behaviours are similar to those of the Baikal seal's Arctic relatives, especially the ringed seal. This helps explain one of the most striking things about the Baikal seal. Although it now lives in freshwater, it still behaves in ways that reveal where its ancestors came from. It is not a freshwater mammal in the general style of an otter or a beaver. It is a seal that kept a cold, ice-associated way of life while shifting into a lake. That is why the species feels so particular. It is not just any pinniped that somehow tolerated Baikal. It is the descendant of ice-loving northern seals that found in Baikal enough of the right conditions to survive, then enough isolation to become its own species. The claws are a lovely example of that adaptation becoming even more specialised after the lake transition. The 2024 genome study notes that pagophilic sea ice-preferring Arctic phocids have large claws used to maintain breathing holes in ice, but says Baikal seals face hard freshwater ice and have evolved even stronger claws, followed by those of the ringed seal, which typically deals with softer and less dense sea ice. That is one of those small details that tells a large story. The lake did not merely preserve an Arctic seal, it modified one. Once the species was in Baikal, the demands of freshwater ice pushed the adaptation further. The seal is, in that sense, both inherited and remade. You can see the same pattern in breeding. Baikal seals are strongly tied to winter ice. Britannica notes that during the colder months they cut breathing holes in the ice with their claws before making feeding dives, and Science Direct's Marine Mammal Encyclopedia summary says females give birth in snow-covered layers excavated in the lake ice, where newborn pups remain out of the water for the first 2 to 3 weeks. The same source says pupping occurs from mid-February to the end of March, and that pups are weaned in 2 to 3 months. So the lake ice is not simply a seasonal inconvenience for the seal, it is nursery, shelter, mating ground, resting platform, and part of the entire reproductive calendar. That dependence on ice makes the Baikal seal feel even more like a preserved Arctic memory inside a freshwater lake. Pups are born with white woolly coats, according to Britannica and Science Direct, which makes obvious sense in snowy layers. Adults remain strongly associated with the ice through winter and spring, and molting also takes place on the ice or on late spring haulouts as conditions change. These are not random habits. They are the seasonal logic of a seal whose life cycle still turns around frozen surfaces, even though the water beneath those surfaces is not the sea. Then there is the question of size. Baikal seals are among the smaller true seals. Britannica gives adult length at about 1.2 to 1.4 metres and body mass around 50 to 130 kilograms, with males slightly larger than females. Science Direct's Encyclopedia summary gives a similar size range and calls them one of the smallest true seal species. That modest size turns out to matter more than it first seems. In the 2020 PNAS study on their foraging, researchers argued that the species' small body size helps make feeding on tiny amphipods energetically worthwhile, something that would be much harder for a larger aquatic mammal. So even the seal's scale appears to have become part of its Baikal solution. Because this seal did not simply adapt to the lake physically, it also adapted to the lake's food web in a way that is frankly a little eccentric and very effective. Britannica says Baikal seals hunt longfin Baikal sculpin, Golomyanka, other fishes, and invertebrates, and can dive up to 400 metres while holding their breath for up to 40 minutes. That alone would already make them well suited to Baikal's vertically structured world. But the really interesting twist is their use of tiny endemic amphipods, especially Macrohectopus branicki, the The 2020 PNAS paper reports that Baikal seals possess highly specialised comb-like cheek teeth that allow them to expel water during high-speed foraging, making these otherwise tiny prey profitable. The authors found very high prey capture rates, showing that the seals can make a living not only by hunting fish, but also by repeatedly targeting small pelagic amphipods. That feeding style helps solve another part of the mystery, which is how a relatively large predator can thrive in an oligotrophic, cold, freshwater lake. The answer is that the Baikal seal is not forced to sit at the very top of a long, inefficient food chain every time it feeds. The 2020 PNAS study argues that by eating amphipods directly, the seals effectively shorten the trophic pathway and avoid some of the energy losses that would occur if they relied only on fish that had already eaten those crustaceans. That is a very Baikal kind of solution. The seal thrives not by being large and dominant in a broad generic sense, but by fitting neatly into the lake's already strange endemic food web. Its teeth, body size, dive behaviour, and prey choice all line up with the local ecology. There is a pleasing irony in that. The most unexpected animal in the lake turns out to be one of the most precisely fitted to it. A visitor might look at the seal and think it is the least likely resident of all. Evolution, which does not care about first impressions, has turned it into one of the most efficient users of Baikal's resources. The species feeds on Golomyankas and Sculpins that evolved within the lake, but it can also exploit the endemic amphipod swarms that link the planktonic world to higher predators. It breeds on the ice that defines the lake's winters. It uses claws adapted to hard freshwater ice. It dives in the same cold, oxygen-rich vertical system that shaped the fishes beneath it. The mystery is not why it persists now. The mystery is only how the first ancestors got in. After that, Baikal makes increasingly good sense of the seal. Its social life also fits the lake's demands rather than human expectations. Britannica says the seals are largely solitary outside the mating season. Science Direct Summary likewise describes them as generally solitary, except during certain haul-out periods in summer and on spring ice. This is another useful reminder that the Baikal seal is not a circus of crowded rookeries and surfline drama. Much of its life is quiet, underwater, and dispersed across a huge inland lake. The 2023 genome paper notes that they spend 80 to 90% of their time underwater, which is one reason population estimates are difficult. A creature that lives mostly below the surface in a lake this large can remain both famous and surprisingly hidden. Even its population history has an unusual shape. The 2024 genome-wide study found that Baikal seals have genetic diversity comparable to other seal species despite long isolation, and the 2023 genome study notes census estimates in the broad range of roughly 82,500 to 115,000 in some recent counts, with the species recognised as stable and of least concern in the IUCN framework cited there. That does not mean the seal is free from risk. Britannica points to pollution, disease history and climate change as long-term concerns, especially because changing ice conditions could affect breeding and feeding. But it does mean the species is not a ghost relic barely hanging on. It is, at least for now, a substantial apex predator in the lake. The disease history is worth mentioning because it adds a sober note without changing the larger wonder of the animal. Britannica notes that a canine distemper outbreak in the late 1980s killed about a tenth of the population, and it also mentions concerns about chemical pollution and warming-related loss of ice. A seal that depends on winter ice for pupping and nursing cannot be completely indifferent to the duration and thickness of that ice. The same logic that once helped it settle so successfully in Baikal could become a vulnerability if the lake's seasonal structure changes too far. The mystery of how the species got here is an old one. The mystery of how stable its future will remain is more modern. Still, when you stay with the animal itself rather than its threats, the Baikal seal remains one of the most satisfying examples of local adaptation on Earth. It is not merely a seal in a lake. It is a species whose ancestry points north to the Arctic, whose closest living relative is the ringed seal, whose breeding still depends on snow layers and breathing holes, whose claws are strong enough for hard freshwater ice, whose dives match the lake's depth, whose prey are largely endemic, and whose teeth have become specialised enough to let it make a meal of tiny amphipods at remarkable speed. Almost every part of its biology carries a trace of both histories at once, the inherited Arctic one and the deeply local Baikal one. That is why the seal feels mysterious even after the science becomes clearer. The facts do not remove the wonder, they sharpen it. A ringed seal-like ancestor enters a freshwater system sometime in the Pleistocene. Isolation follows, ice remains. The lake is deep, cold, and full of endemic prey. Over long spans of time, the descendant becomes not a stranded marine mammal, but a Baikal mammal. The mystery in the end is not only historical, it is also evolutionary. It is the mystery of how thoroughly a place can rewrite an animal without erasing where it came from, and once you reach that point, the seal begins to feel less like an exception and more like the clearest proof of what Baikal has been doing all along, because if even a pinniped can enter this lake and become that local, then the broader answer to why so many species exist nowhere else on Earth is already waiting in the water around it. By the time you reach this point, the question starts to change shape. At first, it sounds like a question about a list of unusual animals. Why does Baikal have a transparent fish, a freshwater seal, giant sponge forests and amphipods that seem to have treated the lake as an invitation to become almost anything at all? But the deeper answer is not a list. It is a process. So many species exist nowhere else on Earth because Baikal has spent an almost unreasonable amount of time giving life the exact conditions needed to separate, specialise and stay local. UNESCO's overview says the lake is about 25 million years old, the deepest in the world at around 1,700 metres, and famous precisely because its age and isolation produced one of the richest and most unusual freshwater faunas on Earth. That is the short official version. The longer version is what all the creatures in this story have been quietly demonstrating. The first part of the answer is time. Most lakes do not last long enough in geological terms to become true evolutionary workshops. They form, they change, they fill with sediment, they drain, they freeze over in severe ways, they shift or they disappear before local life has had enough time to branch deeply. Baikal did not do that. It remained. And because it remained for millions upon millions of years, populations living there were not only able to survive but also to diverge. Ancient lake research treats systems like Baikal as classic settings for explosive speciation and endemic radiations, precisely because they offer a rare combination of long continuity and ecological opportunity. In other words, Baikal did not merely host species, it gave them time to become different from one another. That time would not have mattered as much without isolation. UNESCO's description ties Baikal's extraordinary freshwater fauna directly to age and isolation together, and that pairing is important. A habitat can be ancient and still not produce many endemic species if its populations remain too thoroughly mixed with outside ones. Baikal, by contrast, functioned as a distinct inland world. Species could arrive, certainly, but once established they were living in a basin whose conditions were so specific and whose communities were so unlike those of surrounding Holarctic waters that local evolution had room to take over. The 2019 Amphipod genetics paper says Baikal's highly diverse endemic animal communities are confined to the lake and distinct from nearby water systems, which are inhabited by fauna common across the whole Arctic. That is a very neat summary of what endemism actually looks like in practice. At some point, the lake stops reflecting the outside world and starts reflecting itself. Then there is the issue of space, which is easy to underestimate because people hear lake and imagine one environment with one set of conditions. Baikal is not like that. It is a giant, vertically layered, internally complex freshwater system. It has literal shallows, rocky zones, soft bottoms, different basins, pelagic water, deep benthic habitats, and a bathymetric gradient so large that life can sort itself by depth in ways impossible in ordinary lakes. The recent Sculpin review describes habitat depth as a major abiotic factor in the lake's radiation, and it notes that Baikal's endemic sculpins occupy ecological niches ranging from shallow water to the abyssal zone at 1,642 metres. That is one of the central answers right there. A species in Baikal does not merely have one or two ways to live, it has many possible niches to enter, and over millions of years those niches can be filled by lineages that become more and more particular to them. Depth matters even more because in Baikal the depths are usable. In most freshwater systems, very deep water is biologically limiting for a simple reason: oxygen. In Baikal, oxygen remains available throughout the water column. The 2025 Sculpin paper describes oxygen concentrations of roughly 9 to 14 milligrams per cubic decimeter and says bottom water saturation rarely falls below 70% because of the lake's deep water renewal. That is an extraordinary condition for such a deep lake, and it means the lower waters are not an empty basement beneath the real ecosystem. They are part of the ecosystem. Once deep water becomes habitable, evolution gains an enormous extra dimension to work with. Baikal is, as one recent paper puts it, the only freshwater reservoir possessing a rich deep water fauna. That alone goes a long way toward explaining why so many local forms emerged there and not in an ordinary shallow lake elsewhere. So the lake had time, isolation, and an unusually large menu of habitats. Add ecological opportunity, and the answer becomes even clearer. Ancient lake reviews repeatedly point to ecological opportunity as a trigger for the diversification of invertebrate radiations and species flocks. The 2020 paper on ancient lakes says high species diversity and endemism in such systems are largely attributed to in situ speciation that gives rise to closely related endemic groups, often called species flocks, and it argues that initial diversification was probably triggered by ecological opportunity. That means Baikal was not simply collecting species from elsewhere, it was generating them on site. A lineage would enter the lake, encounter open ecological roles or poorly occupied habitats, and then diversify locally. Over time, that produces not just one endemic form, but whole clusters of related endemic forms. The amphipods are one of the clearest examples of this. Baikal is famous for them because their diversity is both enormous and very obviously local. The 2019 Amphipod speciation paper says more than 350 amphipod species and subspecies are known from the lake, all showing considerable ecological and morphological diversity. The 2017 transcriptome-based phylogeny paper on endemic Baikal amphipods describes their radiation as fast speciation, accompanied by frequent episodes of positive selection. That is very important. It means we're not just dealing with many named forms collected by particularly enthusiastic taxonomists. We are dealing with a real evolutionary radiation, one in which selection and specialization have repeatedly shaped local lineages. Some became pelagic, some remained benthic, some evolved armour, spines or reductions in sensory structures. Some adapted to low temperature, high pressure, or the lake's low mineral waters. Baikal did not merely keep amphipods alive, it turned them into one of the best examples anywhere of how a freshwater lineage can branch, when given enough time and enough ecological room. The same is true of the sculpins. Recent work describes roughly 40 endemic sculpin species occupying a wide range of niches across the lake, with habitat depth repeatedly highlighted as a major driver of their diversification. The 2025 review says this radiation involved dramatic changes in skeletal elements, sensory systems and reproductive mode, all associated with movement into different parts of Baikal's environment. That matters because it shows that endemism in the lake is not one isolated accident. It is a repeated pattern. Amphipods do it, sculpins do it, sponges do it, Even the seal, though not irradiation in the same sense, becomes a deeply local species after entering the system. The more groups you examine, the more Baikal seems to have one broad evolutionary habit. It encourages immigrants or resident lineages to stop being generalists and become Baikal things. Another part of the answer is that speciation in Baikal has not necessarily always been finished and sealed off in some distant past. The 2019 Amphipod paper found highly location-specific haplogroups within endemic amphipod species and reported genetic differences so large in some cases that they approached or matched interspecific differences, suggesting cryptic species or ongoing divergence. It also linked these patterns to geographic features such as the Angara outflow and the Selenga delta, which can act as dispersal barriers inside the lake. That is a wonderful reminder that endemism is not only the result of ancient separation from the outside world. It can also arise from partial separation within a single large lake. Even inside Baikal, populations have had enough distance, enough habitat difference, and enough barriers to begin splitting further. In that sense, the lake has been generating local uniqueness at multiple scales at once. This is where people sometimes expect one grand dramatic explanation, but Baikal does not really offer that. It offers accumulation, harsh but stable cold conditions, great depth, rich oxygen at depth, strong seasonality with ice, clear water, a long narrow basin with different regions and shore types, rare geological continuity, periods of connection and disconnection, refugia during difficult climatic episodes. Ancient lake literature notes that speciation in these systems can involve allopatric, parapatric and sympatric components rather than one single simple mode, and Baikal seems to fit that broader pattern. Some lineages likely split because different habitats reduce contact. Some may have diverged within the same broader basin while using different ecological roles. Some probably kept changing through a mix of geography, selection, and time. So many endemic species exist there not because one thing happened, but because many small evolutionary opportunities kept happening for millions of years. There is also a quieter reason that deserves attention. Baikal's environment does not make life easy for casual newcomers. Cold water, long ice cover, unusual depth, low mineralization, and specialized local food webs all raise the bar for survival. The 2017 Amphipod phylogeny paper notes possible adaptation to low temperature, high hydrostatic pressure, and calcium-deficient low mineralization waters in certain endemic lineages. That is not the kind of setting where any ordinary freshwater species can drift in and feel immediately at home. Local specialists, by contrast, have had generations to adjust to precisely those conditions. So Baikal's environment does two things at once. It creates ecological opportunities for diversification, and it helps protect those local outcomes by making invasion and replacement harder. A specialist lake tends to stay full of specialists. The lake's sheer size amplifies all of this. UNESCO's summary notes that Baikal contains about 20% of the world's unfrozen freshwater reserve. That is not merely an impressive statistic to mention in a documentary voice. It also means the system is vast enough to support large populations, many habitat types, and a complex internal ecology. Large persistent habitats give evolution more room to work than small temporary ones do. They allow separate populations to persist instead of vanishing, and they make it more likely that rare new forms can survive long enough to become established. Ancient lake studies have long treated size, longevity, and ecological heterogeneity as important ingredients in speciation, and Baikal combines all three in a single freshwater body. That combination is rare enough that the lake has become one of the world's great natural laboratories for studying how biodiversity forms. The phrase world apart starts to matter here in a very literal sense. When UNESCO calls Baikal the Galapagos of Russia, it is pointing to exactly this mechanism. A physically isolated, long-lasting environment in which lineages can become distinct instead of being constantly homogenized. And because Baikal is freshwater, not oceanic, That distinction has exceptional scientific value. It shows that you do not need an island chain in warm seas to produce radical endemism. You can also get it in a cold inland lake if the lake is old enough, deep enough, varied enough, and stable enough. The lake becomes less a location and more an engine. It takes lineages in and, given enough time, returns them as something more local than before. That engine has been especially productive among invertebrates, which is another reason Baikal can surprise people. We are often trained to notice large vertebrates first, but much of the lake's endemic richness sits in smaller animals. UNESCO's older site documents describe hundreds of amphipods, many flatworms, endemic copepods such as Epischura baikalensis, endemic sponges, and unusual mollusks and annelids. This matters because smaller organisms often respond more quickly and more finely to local ecological niches. A little shift in depth, substrate, water movement, food source, or predator pressure can become enough to start shaping a separate lineage. Over millions of years, those small differences accumulate into a fauna that looks extraordinarily crowded with local experiments. Baikal is not full of endemic species by accident. It is full of groups for which the lake provided many ways to become local. There is even a sense in which Baikal's endemism contains its own momentum. Once a lake develops a distinctive endemic food web, later lineages entering or evolving within it are no longer adapting to generic freshwater conditions. They are adapting to a Baikal system already built by earlier endemic forms. The copepods, pelagic amphipods, oilfish, sculpins, sponges and seals are all responding to one another as well as to the water itself. A lineage that evolves later is shaped not just by temperature or depth, but by the fact that the prey base is local, the competitors are local and the predators are local. Endemism builds upon endemism. One generation of uniqueness makes the next generation more likely to be unique as well. That is one reason Baikal can look so internally coherent. Its species do not just live side by side. They are products of the same long local conversation. And still, it would be too simple to imagine the lake as a perfect, uninterrupted paradise of diversification. Ancient systems go through stress. Climate changes, water levels fluctuate, ecological crises happen. One search result summarising work on Baikal and nearby Lake Hovsgol argues that endemic species in Baikal likely survived severe glacial ecological disruptions in refugia and later repopulated the lake. Even if the details of those ancient events remain debated, the larger point is reasonable and well supported by the lake's present biodiversity. Baikal's endemic lineages were not only generated over time, they were also preserved through time. The lake had enough continuity and apparently enough internal refuge to keep evolutionary history from being erased every time conditions turn difficult. That is perhaps the best way to answer the question in plain language. So many species exist nowhere else on Earth, because Lake Baikal has acted for millions of years like a place where difference can start, survive, and accumulate. Difference can start because there are many habitats. Difference can survive because the lake is large, old, and relatively isolated. Difference can accumulate because lineages are not constantly reset by extinction, or by overwhelming gene flow from the outside. Put those conditions together long enough, and endemism is not surprising anymore. It becomes the expected outcome. That does not make the individual creatures any less astonishing. It simply changes the kind of astonishment. The seal is no longer surprising as an isolated oddity. It becomes one more expression of Baikal's power to localize life. The transparent Golomyanka is not a random curiosity. It is what a deep, cold, pelagic fish can become in this lake. The sponge forests are not decorative accidents. They are what a freshwater sponge lineage can become when given stability and room. The amphipods are not an overgrown side note. They are what repeated ecological opportunity looks like when it is allowed to run for a very long time. Every famous Baikal organism is really a chapter in one larger answer. And once you see that larger answer, the lake begins to feel slightly different. It is no longer just a place with rare species. It is a place that reveals how rarity is made. Not through magic, not through sudden leaps, and not because nature occasionally decides to be theatrical, though it certainly has that effect. Rarity is made by persistence, by ecological opportunity, by isolation, by harsh conditions that reward specialization, and by enough time for the ordinary work of evolution to become visible in extraordinary forms. Baikal is one of the clearest places on Earth where that whole process can still be seen in the living present. So when we ask why so many species in Lake Baikal exist nowhere else on Earth, the answer is that the lake has not spent 25 million years being just a lake. It has spent that time being a generator of local life, a keeper of deep habitats, a filter against generalists, and a stage on which species could become more and more precisely themselves. The creatures are rare because the conditions that made them are rare, and that very naturally leads to the final stretch of the story, because once a place has been doing that for so long, it begins to teach something larger than zoology about time, survival, and how life changes when the world around it remains patient enough. And after all of that, after the transparent fish, the pelagic amphipods, the sponge forests, the deep water sculpins, and the freshwater seal that still carries a trace of the Arctic in the way it breathes beneath the ice, the lake leaves you with a larger lesson than a simple list of rare species. What Lake Baikal teaches is not only that life can become strange, it teaches that life becomes precise when a place lasts long enough. Baikal is the oldest and deepest lake in the world, holding about 1/5 of the planet's unfrozen surface freshwater, and UNESCO points to its age and isolation as the reason it developed one of the richest and most unusual freshwater faunas on Earth. That is the starting point, but it is also the wider lesson. Uniqueness does not appear out of nowhere. It builds slowly when time, isolation and habitat keep working together for millions of years. One of the clearest things Baikal teaches about life is that survival is not the same as toughness in the loud dramatic sense. We often talk about survival as though it belongs only to the strongest, the fastest, or the most aggressive. Baikal suggests something quieter. Survival, over the very long term, belongs to whatever fits the place closely enough. In this lake, that meant lineages able to live in cold water, make use of deep oxygenated habitats, tolerate long seasonal ice, and adapt to a food web built by endemic plankton and invertebrates. A recent review of Baikal's sculpins describes them as diversified across all depth zones, including the abyssal zone, and shows that deep specialists evolved different molecular solutions for energy use and structural maintenance in high-pressure, dark freshwater habitats. That is not brute force, it is fit. That is worth staying with for a moment, because it changes the emotional shape of the lake. Baikal is not a story of one heroic creature conquering a hostile environment. It is a story of many lineages slowly matching themselves to the same demanding place in different ways. The seal matched itself to the ice, the dives, and the prey base. The Golomyanka matched itself to transparent cold pelagic life. The amphipods matched themselves to nearly every useful corner of the lake. The sponges matched themselves to fixed filtration and habitat building on the bottom. The tiniest plankton matched themselves to clear cold water and seasonal bloom cycles. In Baikal, life did not win by becoming generally powerful. It won by becoming locally exact. The lake also teaches something very plain about time. Human beings are not especially good at thinking in millions of years. We say a number like 25 million, and then continue speaking as though we have understood it, but in practice we have only nodded politely in the direction of something too large to feel. Baikal helps make that timescale more concrete because the time is still there in living form. You do not need to imagine all 25 million years at once. You can look at what they produced. An endemic seal, endemic sponge lineages, hundreds of endemic amphipods, a deep water fish radiation occupying vertical habitats that most lakes do not even offer. Time becomes visible in the bodies of the species that remain. That may be the most practical lesson of all. We usually think of time as something that erodes, wears down, and removes. In Baikal, time also accumulates. It stores difference. It lets small separations become large ones. It gives populations enough generations for local habits to turn into local anatomies to turn into local species, and local species to become local ecosystems. UNESCO's description of the lake as the Galapagos of Russia is not just a pleasant phrase. It is an acknowledgement that this is what long isolation plus long continuity actually do. They allow life to keep becoming more itself in one place, and less like life elsewhere. Baikal also teaches that small creatures are never truly small in ecological importance. That lesson comes up again and again in the lake. The water remains so clear in part because endemic plankton such as Epischura baikalensis help maintain that purity. The food web works because primary production and grazing are handled by organisms most people would never notice from a boat. The larger predators depend on tiny crustaceans and copepods already doing their work below. Even the seal, the animal that looks most likely to dominate the story, turns out to be tightly linked to very small endemic prey. In a place like Baikal, the smallest residents are not background details. They are the operating base of everything else. There is another lesson in that, one that extends well beyond this lake. People tend to notice ecosystems from the top down. We notice the animal with the face, the fur, the eyes, or the body large enough to fit comfortably on a poster. Baikal keeps correcting that habit. It says very calmly that a lake may be held together by plankton, by tiny grazers, by microbial partners in sponge tissue, by the ordinary repeated filtering and feeding of creatures too small to become symbols. This is not unique to Baikal, of course, but Baikal makes it unusually obvious because its famous larger animals are so visibly dependent on its minute endemic base. It also teaches that difficult conditions do not automatically reduce life. They can refine it. Cold water, long winters, deep darkness, and strong seasonality sound at first like a recipe for scarcity. Yet in Baikal, those same conditions helped produce specialization. The key is that the difficulty was paired with stability. The lake remained cold for a very long time. It remained deep for a very long time. It remained structured and partly isolated for a very long time. In such a setting, demanding conditions do not simply eliminate life, they sort it. They reward whatever can solve the local problem, then reward it again, generation after generation, until the solution becomes unusually sharp. That is why the species in Baikal often feel so complete. They do not look halfway adapted. They do not look temporary. They look as though they belong. Even the seal, which sounds improbable in a freshwater lake until you learn its history, ends up feeling entirely consistent with the place once you understand the ice, the prey, and the long isolation from its ringed seal relatives. The same is true of the Golomyanka, the Sculpins, the Amphipods, and the sponges. Baikal teaches that belonging is something evolution can build very slowly, until a species seems almost unthinkable anywhere else. At the same time, the lake teaches something more sobering. Ancient does not mean invulnerable. Baikal has lasted for millions of years, but that does not place it outside the reach of modern pressure. Scientific work on the lake has documented warming surface waters, stronger thermal stratification, shorter ice cover, long-term shifts in plankton depth distributions, changing nutrient supply to the photic zone, and coastal eutrophication tied to both climate effects and human activity. A 45-year plankton study found steadily increasing surface temperatures and changing vertical positions of major plankton groups, while a PNAS paper on nutrient cycling reported unprecedented recent increases in nutrient supply to the photic zone and growing uncertainty about the resilience of the lake's highly endemic ecosystem. That matters because Baikal's uniqueness was built under very specific conditions. When those conditions begin to shift, even gradually, the species most precisely fitted to them may not remain secure simply because they are old. In fact, specialization can become a vulnerability when the environment changes quickly. A 2021 study of the coastal zone reported that the role of endemic species in total biomass has been decreasing in some impacted areas as warming and human influence alter community composition. While a recent UNESCO State of Conservation report says that scientific bodies in 2024 were still actively addressing eutrophication of the coastal zone, wastewater problems, ecosystem monitoring, forest management, and threats to aquatic biological resources. In other words, Baikal is still a place of long natural time, but it is now also a place under short human time. That contrast may be the hardest lesson the lake offers. Nature can be patient. Human pressure usually is not. Evolution took immense spans of time to produce these species. Pollution, shoreline development, altered nutrient flow, and climate warming can disrupt parts of that system in a tiny fraction of the same interval. The lake's age can make it feel permanent, but permanence is not the same as immunity. UNESCO's site materials and official reporting continue to describe pollution, wastewater treatment, ecosystem monitoring, and legal protection as live issues, which makes the conservation message very simple. A system this old can still be damaged quickly. There is also a scientific lesson here that is easy to overlook because the lake is so beautiful and so full of memorable creatures. Baikal is not valuable only because it is beautiful or rare. It is valuable because it shows processes that are usually hard to watch at this scale. It shows what old age does to a freshwater ecosystem. It shows what isolation does. It shows what ecological opportunity does when it persists instead of vanishing. It shows that deep freshwater habitats can produce specialized radiations much as oceans do, and that life in a stable but demanding place can become both diverse and narrowly adapted. That is why Baikal matters so much to evolutionary science. It is not simply unusual, it is explanatory. And for anyone listening without a notebook open, without a research plan, and without any immediate intention of measuring plankton under the ice, the lake still offers something more general and more human. It shows that survival is often cumulative, not dramatic, not clean, not one grand victory, just a long chain of workable adjustments held together over time. One lineage gets slightly better at depth, another at cold, another at filtering water, another at breeding under ice, another at moving through darkness. Eventually those adjustments become a world. That is what Baikal is. Millions of years of workable adjustments layered together until the whole lake feels unlike anywhere else on Earth. It also has a way of correcting the scale at which we usually think about importance. Human attention is often drawn to the immediate and the visible. Baikal asks for a larger frame. It asks you to remember that a transparent fish matters because of the tiny prey beneath it. A seal matters because of the ice, the fish, the amphipods, and the history that brought its ancestors inland. Sponge forests matter because stillness can reshape a habitat. Ancient water matters because age changes what evolution is able to do. Nothing in the lake stands alone for long. Each part carries the others. There is a plain comfort in that too, not sentimental comfort, just the steady kind that comes from seeing a system where complexity did not appear by accident, and where even the strangest forms belong to a chain of causes you can actually understand. Baikal can feel mysterious at first, but its mystery is not vague. It is made of cold water, time, isolation, depth, oxygen, ice, food webs, and repeated adaptation. The more you learn, the less the lake feels magical, and the more it feels precise. Oddly enough, that makes it even more impressive. A place does not need fantasy to exceed expectation. It only needs enough time to become exact. And perhaps that is the final lesson about survival. A living system does not endure by staying unchanged. It endures by changing in ways that still fit the place. Baikal's history is full of that kind of change. Lineages entered, diverged, specialized, and settled into roles that made sense within the lake. The danger now is that the pace and type of environmental change may no longer match the slow, adaptive rhythm that created the system in the first place. When warming, eutrophication, and coastal disturbance move faster than long-evolved endemic communities can absorb them, the old balance becomes harder to keep. That is why protecting Baikal is not just about saving beautiful wildlife. It is about preserving one of the clearest records on Earth of how life and time can work together when given the chance. So as this journey through the lake begins to settle, it helps to return to the simplest image. Cold water in the middle of Siberia. Ice above it for months. Darkness below. Small creatures drifting. Fish rising and falling through depth. Sponges filtering quietly on the stones. A seal surfacing at a breathing hole it cut through hard freshwater ice. All of it happening in a place that has lasted long enough to turn survival into local character. Lake Baikal teaches that life can become very specific when the world around it remains patient, and that once such specificity exists, it becomes something worth protecting with equal patience. And somewhere beneath that clear water tonight, the same work is still going on. Tiny grazers are feeding. Fish are holding their place in the dark. The old lake is still teaching its creatures how to belong to it, one generation at a time.